Okay, we are live streaming.
Ok, anche YouTube sta trasmettendo.
Comunque questo non è la fattura dell'esame, è questione è mezzo perché hanno provato la parte.
Marco, scusa, Marco. Marco, mi senti? Marco, mi senti? Eric, can you hear us?
Yes, do you hear me?
Yeah, very, very well.
Thank you.
So can you try to share your presentation, share your screen?
Okay, where can I click? Shall I click to share my screen?
Is there any button?
Yes, I see it.
Nice.
I just launched the PowerPoint. Yes. Do you see it?
Not yet.
You don't see it?
No.
I click again.
Okay.
Oh, yeah, yes. Oh, yes.
Yeah, now we can see.
Okay, so and
Yeah.
when I switch to presentation mode, it's okay?
Yeah.
Yes.
Yeah, it's okay. For us, perfect.
So now you can disconnect me?
Or yes.
I
Yes,
think
thank you.
I am disconnect. It's okay?
Yeah, it's okay. Thank you.
Thank you very much.
Francesco, ci sei?
Sì, ci sono.
Senti, eventualmente le domande da YouTube le mettete sulla chat, allora.
Sì, ce le copio io. Aspetta.
E se il chair non le riporta, cosa si fa? Le riportiamo, gli
Si
diciamo
chiedono
noi, sì.
noi. Sì, si
Ok,
dicono noi.
vai.
Aspetta, fammi aprire la pagina se riesco.
Good afternoon, everyone.
Hi, Manuel.
Manuel,
Hello, hello.
How are you?
Very well. Teleworking.
Ah,
Yeah,
okay.
it is fine. Yeah, the second wave in Holland is very strong, so we are working from home as much as possible.
Yes, same situation here. In Tuscany from this week
Yeah,
is the same. Okay.
yeah.
so Manuel, can you try to share your screen, please?
Yeah, I can.
Okay, sorry. I will let you share. Okay, can you try?
Yes. Can you see my screen?
Not now. Maybe there is a little bit of delay.
Mm-hmm.
Yeah.
Yes. Fantastic.
Yes. Yeah, we
Good.
see it.
Good.
Perfect. Thank you.
Yeah, you're welcome.
Hi everyone, this is Nemesio.
Hi,
Hi,
Nemesio.
Nemesio. Hi, how are you?
Hi, fine, thank you.
So the same as you, can you try to share your screen as I will allow it? Yeah, you can try now.
Me? Let me
You can
open
try.
PowerPoint first. Maybe I have my presentation here. Okay. Now I have PowerPoint. I will share. I will share just one application as well.
Yeah, we can see it very well.
Perfect.
So perfect. Yeah.
Thank you. I stop.
Good morning, good afternoon, good evening, everybody.
Hi, Jan. Good afternoon.
Thank you.
Hi, Jan.
Hello.
Hello, Jan.
Hello, Simonetta.
Hi, good afternoon.
Hello, Sten.
Yeah, hello, Jan.
Hello, everyone. This is Mauro Pierdicca speaking.
Ciao Mauro.
Ciao, Mauro.
Ciao.
Ciao, ciao.
Jan, can you try to share your screen if everything is fine?
Okay, I'm doing this just right now.
Yeah, it's working fine.
Full screen. Okay,
Yes,
good.
perfect.
So I stop.
Maria Jose, hello? Can you hear us? Maria Jose, can you hear us? You have to unmute yourself.
Yes.
Okay.
Yes, I hear you well. Do you hear me well?
Yeah, we can hear you well. So just for try, if you can share your screen and we see it in the right way, in the right shape.
Mhm. So,
Yep, pretty fine. Good.
okay. So,
Yes.
Hi, Nazareno. Good afternoon. This is Manuel.
Hi, Manuel. Yes, yes.
Can you read the chat?
Yeah, yes. Because okay, I was just asking how to manage this session because, for instance, I'm not sure who's really going to present. I guess that the first Jan will present, and then Maria Jose also is going to present. Manuel, I think you are the third.
Yes.
And so probably we check who's going to give the presentation, Francesco?
Yes, for the check of the video, audio, and so on, we miss already Francois Cabot, if he's here.
Yes.
Okay.
I let you share your presentation.
Okay.
Right. Could you share it? We are waiting for it.
Not yet.
Not yet.
Okay.
Oh, yeah.
Yes, I'm sharing now. Yeah, okay.
Yeah, now it's okay.
Okay.
Okay, nice.
Slow. Okay.
Yeah, it's a little bit, but yeah, let's see what happens. Now we miss the last one is Ilya Sadovsky, that I will let him share.
Yeah, hello, can you hear me? Hello?
Yes,
Yeah.
yes, we can. Hi.
Hello. So you can, yeah, try to share.
It's all right?
Yeah.
It works, yes.
Works fine, yeah.
Okay.
Okay, good.
Good. So for now, the list of the speaker is complete. So we are waiting for the first speaker for the 2 o'clock.
2:30.
2:30, yeah.
Another 20 minutes before.
Sorry, I may have skipped. No, there's no keynote speak today. Sorry, yes.
We have we have the first speaker, then it's Jan.
Mauro, you are asking about how to notify that the 2 minutes left or something like this. You can unmute for a while your microphone. We are now arranged to have all the presenters able to mute or unmute their microphone by themselves. So you can unmute and notify and then...
Just a brief interrupt, okay?
Okay. I possibly is the best solution. I think that some exotic sounds are quite annoying at the end. Ringing or something else is not good. So if I believe if the chair make a small interrupt is better.
Okay.
Thank you.
Thanks. So all participants to the session can make a question directly.
Yes.
Okay.
Yes, we are trying this after the warm up of yesterday. We are trying to do this, and let's see how it will proceed. We believe it's better. And in the meantime, we will try to report the question on chat from the YouTube live streaming. So I will invite also before the beginning of the session the chair to check from time to time the chat. We will try to report on the WebEx chat the question from the YouTube.
Okay.
If possible, we will try to do all that, but it's not so straightforward. So let's see how.
We have not to follow the YouTube
no, we will do
streaming
it
as well.
No,
Okay.
we will do it, and then
Thanks.
in case we will try to report the questions. Okay, I think it's time to start this second day of MicroRad 2020. Welcome to all the participants. And shall we start now? And today we will prosecute the mission session. The schedule foresees 8 presentations before the break and 6 presentations after it. And I have a few recommendations. As you already know, each presenter has reserved a schedule of 10 minutes for presentation and 5 minutes for questions and answers. I would warmly recommend the chairs and the presenters to keep this schedule. It's very important. Please note that, as I already said, all the participants connected by WebEx can mute or unmute their microphones to ask a question directly to the presenters. And if possible, we will also try to report the questions from the YouTube chat. So I would also ask the chairs to have a look from time to time to the chat to see if there are other questions. It is not so straightforward, so we'll try to do it as best as possible. And this session will last at 4:30 p.m. Central Europe time. And in the break between 4:30 and 5 p.m., we will have the pre-session for the second session of the day. And I would invite the presenters to the second session to join for the pre-check of audio, video, and screen sharing. Also, this is very important to ensure a smooth prosecution of the conference. And that's all from my side. I will now leave the floor to Manuel and Mauro for the first session. Thank you, everybody, and enjoy MicroRad 2020.
Thank you, Emanuele. My name is Nazareno Pierdica from University La Sapienza of Rome. I will co-chair this section together with Manuel Martineira, and I will introduce the first 4 presentations. So the session is about current and future missions. And the first presentation will be given by Jan Kerr. And this is about SMOS in 10 years old, but still going strong. So please, Jan, you can share your screen. And sorry if I will briefly interrupt you after 8 minutes of your presentation, just to inform you about the timing.
Thank you very much, Nazareno. And yes, interrupt me. I will give you a quick overview of SMOS. SMOS, when the abstract was written, was 10 years old, but now it's more than 11. So I will try to give you a quick overview of the main things going on with the SMOS. So, of course, now it's getting to be an old story with a proposal which was made to ESA in 1998, so many years ago. But eventually, we are now in the 11th year of the satellite in operation, 12th actually. And all the components are nominal. There is plenty of fuel and power to go on. The one issue we're having at the moment is the degradation of some protective cover of the arms due to age. And apparently, it leads to some overheating, eating of components on one element. This has no impact on the quality of the data, but of course it indicates that little by little the system is aging, and all the different teams are working hard to find solutions that warming up become a bit more annoying. The main thing we can say is that the stability of the instrument has been outstanding, and I will show you a quick slides on this just in a minute. The main issues we have some of them are no issues. One of them is the retrieval quality, which is improving all the time. At the beginning, the measurements were new, the instrument was new, we had many challenges to face. But from versions to versions, the quality of the retrievals have been improving, and I will show you a quick example later on. And now we're at the stage where we are really fulfilling completely the mission objectives, and we have many operational users. A more significant issue is the RFI. As you know, radio frequency interferences do harm the signal. There are unlawful emissions within the protected spectrum. We are trying to reduce it through actions, ESA and other bodies, but also we are developing algorithms to try to filter out some of the RFI. It's detrimental to the quality of the retrievals, but it enables to go in areas where otherwise we couldn't go. So new algorithms are being tested for possible implementation in the future. So now we have 11 years of continuous data, which is unique. For L-band measurements, we cover land, ocean, and cryosphere with many results, very interesting over these different areas. We have operational users, numerical weather predictions, risk assessment, and operations in different domains. And there are many science users with new development in many areas. And of course, many applications now emerging. The next presentation by Maya Ho will show you a number of them. But first, the stability. This is a plot made by François Cabot over Antarctica, Dome C in the central of it. And we expected this ice sheet to be very stable with time. And as you see, for the 10 or so years of the data, we have a very stable signal at repolarization. So you might see these little bumps. Look at the scale, and it's 5K here. Might look not so stable, but if you look when we have both SMAP and SMOS in operation, both of them follow exactly the same movement. So it's really a geophysical signal. It's even more visible on the edge polarization, horizontal, where we have these spikes, which, as you see, it's almost early at the beginning of each year. And the trend, but when we look at the second period, we have another trend, but again, it's completely confirmed by SMAP, two different instruments, two different ways of measuring, two different systems, and all together. So when they agree so well, we know that we are facing a geophysical feature, which means that there as well, there is some science to be done. In terms of retrieval performances, I go here with the example of the Somotia retrieval. And you've got 4 points in this Taylor diagram. You see very familiar with it, with the standard deviation indicated here and the correlation coefficient as the angle, if you want. And you see that number one was the version which is currently available with all, I would say, L1 and L2 retrieval algorithm. And if you go to the 4, which is both with the new L1 and the new L2, which will be released before early next year, you see the big increase in quality of the retrievals we've made by just going from the current version to the one which will be released very soon. So we are still improving the algorithm and the retrievals. So we are making measurements. I give here the example of agriculture, where you see the soil moisture at small scale, roughly. And when you do some disaggregation scheme, you see here the irrigated plots. This is taken in Australia. This to show that the spatial resolution is crucial. You see here one example with the SMOS, so roughly 40 kilometers with spatial resolution. You are not able to address some issues unless you use this disaggregation scheme, which degrades a little the quality of the signal, by the way. So this is something you want to do. We have also very interesting results over the vegetation, where we extract the VOD, the vegetation optical thickness. And you see again here that by disaggregation, showing what gain we can make with the final resolution, on top of the fact that we can measure VOD, and as shown on this plot, you see that there is no saturation at L band as it occurs at higher frequency, C or X band in that case, or even worse with optical channels. So we're able to assess up to 300, say, tons per hectare rather efficiently, when as with other measurements, this is not possible. And I've written there a number of applications which would benefit from this, benefit actually. The main conclusion here is that we have to go towards a higher spatial resolution, not a lower one. An example of this VOD, this map is a 1 kilometer above ground biomass made with SMOS data. And you see that we cover all the globe, and you see the distribution with the areas of very dense vegetation, like in the tropics, to the boreal areas. So we are able to infer very important measurements on the surface. With 10 years...
8 minutes are left. Sorry.
Thank you. With 10 years of data and so on, we can monitor other events. Here you see off-molar plots, one per year from the beginning to 2018. And you see, this is for Australia again, big events in terms of huge rainfall or very dry period indicated by the red, which is a dry anomaly, when the blue is a wet anomaly. And this corresponds to well-known events, such as different floods and impact of the El Nino, La Nina, and other climatic effects. We can also infer rainfall from SMOS data by simply monitoring the evolution of soil moisture. This is work done by Thierry Pellarin at IGE. And you see that we get significant improvement. This is the blue color in all these graphs in terms of correlation coefficient and so on, bias and RMSE, when we're using SMOS to improve the satellite estimates of rainfall. Other applications are looking at fridge thaw, here done by the FMI group. And you see the temporal evolution here of the fridge thaw area on the right-hand side, and on the left-hand side, you see the related methane emissions and the evolution through time. So again, with SMOS now, we're able to monitor these for about 10 years, and this should go on as long as SMOS is operational. Over the oceans, the assimilation of SMOS sea surface salinity improves the prediction. It's for the weak El Nino example, where you see when you assimilate simply the normal data, you are on the top left-hand side, to when you use Aquarius and SMAP, and then on the left bottom, SMOS assimilation. And you see that for the different trials, you are very close to what actually happened. And when you look at the mean forecast, again, the cyan color, SMOS, indicates very good fit with the actual measurements. A big success was also obtained when SMOS was used by the European Center for Medium Range Weather Forecast, ECMWF. And since June last year, they're assimilating SMOS data directly in the model, bringing a few significant improvements in the forecast. And by the same token, they're also releasing now soil moisture in near real time, that is less than 3 hours after sensing. So the community can access near real time soil moisture, and of course, better weather forecast. So to summarize, in spite of its old age, SMOS is still in good shape and not senile, like me. There are a wealth of new applications which have emerged since 2010, and using L-band as, together with Aquarius, SMAP, and SMOS, they have proven the uniqueness of L-band radiometry and the need to continue this type of measurements to avoid any data gap. The next system should have at least the same characteristics as SMOS or SMAP. The spatial resolution ideally has to be improved to satisfy the need of both science applications and many other domains. So improving the spatial resolution is really the next step, which is necessary. I think, considering the 11 years old SMOS and 6 years old SMAP, we desperately need a real follow-on mission to SMOS and SMAP. By real, I mean a mission fulfilling the same characteristics and ambitions. So, as a conclusion, I would say watch out for the SMOS and SMAP new results and discoveries. and the proposed new L-band missions, MOS-HR and Small Next Precursor ULIT, to name two, have to be watched out, and probably we would appreciate if the community could help us push forward such missions. And of course, watch out for RFI sources and help us eradicate them. And I will finish with this slide to thank you all for your attention. And just mentioning that this map has been produced with SMOS. It's a sky map at L-band. And you'll notice the quality of this map. I think it's pretty unique because there are good measurements from ground radiometers, but covering the two hemispheres with such an accuracy and quality, I think it's unique. Thank you very much.
Thank you, Jan, for this overview, and actually 11 years of operation with quite stable performances is very impressive. So we have probably a couple of minutes for questions from the audience. Any question? If not, I will just make a short question. I was interested to the biomass product. Do you have an idea of the quality and which type of validation have you applied to assess the quality of those maps?
So over the tropical areas, it's quite difficult actually to get a good validation. We are comparing to existing maps, those derived by the SACHI and others. We derived above ground biomass maps, and we are fairly consistent with them, with possible improvements, and we're working on it with especially looking at areas of complex mixture of between high trees and small lower vegetation. But currently, we are working with the biomass team, you know, the Explorer mission, which is to be launched in a few years. And the validation is quite significant. We get good results. Of course, with the limitation, when you talk about biomass, of the spatial resolution of 40 kilometers, which in some cases is a bit crude to assess really the changing biomass. Nevertheless, over some areas, we have, such as Amazonia and the Congo Basin, we have very interesting results, which we hope to have published soon on this with the correct validation, I would say.
Okay, thank you very much.
You're welcome.
So if there are no more questions for Jan, I will move to the next presentation that will be given by Maria Jose Escorihuela. I hope I pronounced correctly. And the presentation is about 10 years of SMOS measurements toward climatic applications. Please.
Yeah. Good afternoon. Thank you. Yes, I'm going to present the climatic applications that have emerged thanks to more than 10 years now of SMOS data availability. This presentation is possible thanks to the contribution of many international teams. Not here to mention everyone, but just the PIs of each team. SMOS was launched 11 years ago. Challenge. It was the interferometer in space, consisting of 69 small antennas, to be equivalent to a full antenna of about 8 meters of diameter. With that, we were allowed to have with a resolution better than 50 kilometers, soil moisture over the land, and here we see how it changes across the time. And ocean salinity. Can observe river plumes and eddies. These measurements are available with a better resolution than today's, and crossing time equator is about 6 a.m. p.m. SMOS, there were already methodologies developed to derive soil moisture at higher resolutions. Here we were using the methodology of dispatch to derive 1 kilometer soil moisture. And with more than 10 years of data now, we are also able to provide anomalies of soil moisture. Here we have, as an example, the Ebro Valley. And in these plots, we see the onset of a drought in 2016 over that valley. The high resolution soil moisture anomaly allows us also to study spatial patterns within the valley. And this plot shows the correlation of the anomalies from this point to the rest of the points in the basin. And we see that the spatial correlation changes from this point when this point is considered, which is more Atlantic continental, when this other point closer to the Mediterranean is considered. Another aspect we can study with these anomalies is their relation with other variables that are traditionally used also to monitor drought. For instance, in this case, we see the correlation, the time lag correlation with anomaly of the evapotranspiration. And here, this plot shows the fraction of the basin that is affected. And here is the time lag that we apply to the different data. Basically, what we see is precedes the evapotranspiration anomaly over most of the valley. Scale patterns, spatial patterns have also been studied. So here there was a principal components analysis of the soil moisture studied, and it was found some areas where the correlation with the ENSO is very strong. These are marked in red, and some of them infer a dry pattern and others a wet pattern. Here we can see a dry pattern in Australia, and over Europe and India and Asia is more a wet pattern inferred by ENSO. Similar to what was presented by Jan, but a bit different. So in this plot, we see that optical depth of the vegetation, which is a measure of their water content for L band, saturates at higher values of biomass compared to other microwave sensor, and even much better than optical sensors. This has allowed to monitor the biomass over highly dense forests, like in the tropical regions. In this study of Brandt et al., it was shown a overall decrease of biomass during the years the SMOS was monitoring. Some of them were correlated with a decrease also in rainfall, but not only. In this other study concerning the global tropical areas, there was also monitor decrease in biomass in the overall tropical region. Major innovation of SMOS was to provide ocean salinity, and not only and especially over the Arctic region, where the sensitivity to salinity is lower, and the retrieval of salinity is more challenging. So here we have Greenland to locate ourselves. This is the Arctic, and the same season for across the different years where we have SMOS observations. And we are able to see a number of things that change across the years. For instance, we have the Ob and the Lena river plumes. We have the Beaufort gyre here that changes across the years. And we can also observe the different inflow from from the Pacific, with different inflow of waters across the different years. Oops, I cannot change. Following with the need of the high resolution, as Jan was mentioning, there is mesoscale effects like the eddies that have been monitored with SMOS and were not easy to measure with other lower resolution sensors. Here is a plot of salinity together with the currents, where that indicates the accuracy of the separation between the different salinities and how these eddies influence in the transport of sea surface salinity across different areas. Yeah, it has been also crucial to monitor high-speed winds that were not able to monitor with other microwave sensors that also saturate at lower values of wind speed. Another terrain where SMOS has been breakthrough, it's in the cryosphere. So here we have the sea ice over the Arctic across 11 years of SMOS. And SMOS is the first instrument to be able to measure the thin sea ice. Here we have a plot for the different years and the coverage of sea ice we have for different ranges of sea ice thickness. We observe overall a decrease in the coverage of sea ice for all the thickness, and especially this last year, in 2020, we record a special abnormal low value.
Sorry to interrupt. We have 2 minutes left.
Thank you. Yes, so I'm close to it. Monitor of the free and thaw states allows to monitor the methane emissions. And also here we have an image of Antarctica, similar to other ice caps. Thanks to SMOS, we have complementary information to other sensors about the melt. Yeah, and there is a consistent improvement observed between the modeling at ECMWF and SMOS at both polarizations. So we have seen, we have a large number of unique applications based on SMOS measurements, both in the water and the carbon cycle or related with ocean circulation, very especially also over cryosphere. We recently conducted user-led study that where all these applications were reviewed with the users, and it was shown that the 10 kilometers would be really a breakthrough resolution to advance on these applications. And currently there is a mission in study to provide this resolution. There will be 3 presentations later on this session about this. But apart from that, there is no other. This mission is planned for launch time is a bit far away, so there is nothing yet in between for continue with L1 measurements. So that's it. Thank you very much.
Thank you, Maria Jose. So are there questions or for Maria Jose from the audience? No questions. So, okay, I have just one that is about freeze-thaw mapping. I just was wondering which is the contribution of the multi-angle capability of SMOS to map freeze-thaw changes with respect to, for example, to SMAP? I mean, there is information improvement content from this multi-angle in the algorithm for discriminated freeze-thaw states? Or?
I'm not very familiar with the algorithm. Maybe Jan, can you answer this?
Yes, I can give a quick answer. Actually, the algorithm used by SMOS and SMAP are roughly the same, except that that of SMOS uses the multi-angular capacity to decouple the impact of vegetation on the signal.
Okay. Okay, thank you.
You're welcome.
If there are no more questions for Maria Jose, okay, I think that we can move to the next presentation that will be given by my co-chair, Manuel Martineira. It is about, again, about SMOS and specifically on SMOS instrument calibration and level 1 processor performance after 10 years or 11 years, I would say, in orbit. So, Manuel, the floor is yours.
Thank you, Nazareno. I will share my screen. Can you see my screen?
Yes, Manuel, could you please switch to, to the slideshow?
All right.
Okay.
Thank you, Nathan, again. Yes, my name is Manuel Martineira. I'm working for the European Space Agency, and I will be presenting to you the SMOS calibration level 1 processor performance after 11 years. In the paper, when we submitted it earlier this year, was 10 plus years, but 11 years. I will just give you the highlights of the work done by many people spread across European industries and universities, and that has been enjoying, I would say, enjoying very much these 11 years working in SMOS. It was launched 2nd of November 2009. It is the first two-dimensional interferometer in space. And this means that it has a very wide field of view. It makes images, contrary to a conical scan type of radiometer. This opens many possibilities in the signal processing and also in the retrieval of physical parameters. So people working or used to conical scanning who have jumped, or across scanning who have jumped into two-dimensional interferometry had to make a real effort to go into this, into the wealth of possibilities that this kind of instrument provides. And after 11 years, I would say that people are still finding new ways of signal processing, removing, filtering RFIs, improving strategies, reducing noise. So it's a world of possibilities, this interferometry from space to remote sensing. You heard that besides the soil motion surface energy products with which the mission started, there are other products who have been were now available from our mission: frozen soils, thin sea ice, wind in hurricanes, sea surface wind, and more to come. Now, how do we calibrate SMOS? Going from the top, we make two cold sky views in July and in December, and this allow us to remove some offset in the correlations by the technique that was proposed by Professor Corbella to comply with the conservation of energy principle. And then do some internal calibrations once every 8 weeks to remove instrumental errors. Every 2 weeks, we go again into cold sky views to calibrate the noise injection diodes that will also serve to remove, to obtain the gain and offset of the receivers. Every week, we have to perform short calibration to track the offset variations. And every 10 minutes, we have a 6-second noise injection to follow the local oscillator phase. Now, this plot is important. It shows the sun elevation over the antenna plane, the horizontal axis, versus the physical temperature of the receivers in the vertical axis. And in the green area is where the instrument is when nominal pointing, when looking down to the Earth. So we are between 4 Celsius and 29 Celsius. While when we flip the instrument to look to the cold sky for calibration, we are normally in a lower temperature range, as you can see here in the cold calibrations here. And therefore, we have made an effort since 2014, and very recently in June and in November this year, to make calibrations, letting the sun elevation to go higher and higher above the antenna plane. Of course, we have to work out the signal of the sun and remove it to make the calibration right. But as you can see, now we are falling in the green band, where is the instrument physical temperature actually when the instrument is pointing to the Earth. Some words about the level 1 processor. We are running version 620 since 2015. But version 724 has been delivered already in October last year, and will be deployed in April, May of next year. We are now reprocessing what we call the third mission reprocessing data from the very beginning up to now. And once this has been achieved both at level 1 and at level 2 for solid, in other versions, 740, 750, and to have further improvements in the future. Now, what this new version that will be operationally available very soon will bring: improved stability, especially during the eclipse season in our boreal winter, and the implementation of the so-called all-SF mode, which is a simpler mode of calibration of the array, a better sun correction, both when the sun is in the back of the instrument and also in the front, and also improvement of radio frequency interference flagging. The next version, 740, will enhance further the RFI filtering, and I will show an example of this, which is very promising, and also will contain the first implementation of a sun range temperature estimation aligned with the radio telescopes. Maybe it sounds strange, but because of the very wide field of view of SMOS, we are imaging the sun, and we have realized that we can provide this useful data to scientists of the solar sciences. Now, version 750, which will come even later, will apply super sampling method for a better sun removal, also more improved RFI filtering, and the first prototype of the sun brightness temperature estimation product that should be ready by 22. And in the pipe, we have version 760, in which we are already working, that will make use of these new hot calibrations I just mentioned before that were carried out in last June and November. Now, just to give you some results on the stability. So on the left, you see the current version, and on the right, the new one that is coming. I've studied this portion of the Pacific Ocean in the box here, and you can see through the more or less 10 years span of this data set that we have reduced both seasonal and long-term variations. Also, in the Pacific, we are evaluating the performance of the algorithms, and we see the new version also having smaller seasonal variations. With this stability, some scientific results about stratification of water, which are compatible with global warming, have been are right now under study. We wanted to know if these residual slopes over the ocean were instrumental or were geophysical. So we look at Antarctica, which should be a more stable target, to find out. And this is what we got. Well, we got for both versions, the current version and the new one, a very stable signal over Antarctica, over all these tracks in black here, which are close to Dome C, where IFAC has a ground station with an L1 radiometer, which allows us to track and monitor trends in a small compared to this ground-based DOMEX radiometer. And then we realized that as from 2018, and we were very surprised about this, the brightness temperatures are going up both in both polarizations, X and Y. Y not so much, but still. And then we thought, okay, what is this? Is this something to do with our payload? And we have cross-checked with AMSER, and AMSER, this and X-band of AMSER also show this trend, and also SMAP. So something is happening in Antarctica related to the warming of the ice sheet. And now scientists, ice matters are looking to this evolution over Antarctica. Overall, in this table reflects a number of key parameters for the current and for the future version. And you see green in all the parameters that we are improving. We look to the long-term slope in different polarizations, Stokes 1. The latitudinal slope has to do with orbital variations. Also, the difference between ascending and descending brightness temperatures. This is a quality also parameter that is important. The biases with respect to models, and also the seasonals. So we are improving in our parameters. Just a glimpse of this RFI filtering that will come with the version 740 that will come in a future time period, probably 2022. So we have been able, by signal processing of the visitities, to remove or filter the effect of the RFI. There's always damage, there's always a loss, but the degradation is less when applying this algorithm. So this is also good news, and we will be validating this algorithm up to level 2. So in conclusions, ESMOS have been planned for 3 years as a 3-year mission with 5-year consumables, and it's now just more than 11 years. So we are very happy about this, especially because of the data record that has been acquired and is helping scientists to do all kinds of studies. and now more related to climate change. Both the payload and the platform are in good health, but we have seen some degradation in the hardware, thermal hardware of MicroRad of the payload. It's not serious. It's something that we think for the next 2 years there is no problem, and we are working on possible strategies to limit these effects. About the calibration and data processing, we are still improving. The climatology signatures and the operational processor version 7.24 is expected to be deployed in April, May 2021. And the focus of this has been RFI filtering, and after this new version, improve cold sky calibration, cold sky measure map, new products like the sun flux and the top content of the ionosphere, and a better sun correction, reduce spatial ripples. Thank you for your attention.
Thank you, Manuel, for this presentation of the status of the instrument and the system. We have just 1 minute for questions, if there are questions from the audience. It seems there are no questions. Since it is 15 past 2, probably we can move. It is time to move to the next presentation that will be given by Francois Cabot, and the title is Distributed L-Band Interferometry Demonstration Mission. So, Francois, please, you can share your screen. Okay.
Do you see us?
Probably can switch. Okay, fine.
Okay, good. So I will give you a status on this future mission that is aimed at demonstrating our capacity at using unconnected antennas for L-band interferometry. As an introduction, of course, I will not linger on the SMOS heritage. Thanks to the 3 last papers, you have seen a lot of SMOS benefits and the uniqueness of passive measurements at L-band for both terrestrial and oceanic surfaces. So I will not insist on the pros, which have been demonstrated already, but just emphasize a bit on the cons, which with the first one being the spatial resolution. This has been already addressed several times, and this is mainly linked to the diameter of the antenna and, of course, the wavelength at which we operate. To address this question, we have different options. Larger interferometer or larger physical antenna, such as was tested for Aquarius and SMAP, with different price tags, and but they share also the same concern with the radio frequency interferences. Just to emphasize a bit the various merits of both technology. Of course, the real aperture offer systematically an excellent sensitivity. The demonstration, the spectacularly demonstrated RFI mitigation technique has been proven by SMAP results. But on the minus side, of course, you need a large mobile structure and some complexity with the orbit maneuvering. On the other hand, interferometric radiometer offer higher spatial resolution available because it's scalable. The payload is modular, that is constituted of many small similar instruments. It offers a directional capacity, which hasn't been underlined very much, but it's clearly a plus if you want to separate, as Jan said earlier on, the signals from the vegetation and from the surface. But of course, on the minus side is that the radiometric accuracy rapidly decreases with the extension of the dimension of the interferometer. So, given that we operate at the same wavelength and we aim at a higher resolution, of course we face similar challenge. But the interferometry has a capacity to go unconnected if we envision that each antenna to be carried separately on different spacecraft. So that takes the structure complexity at minimum, the coupling between antennas as well. But of course, it will make orbital control more challenging and most probably much higher complexity on ground processing of the data. We already have an instrument simulator, which we use to demonstrate the concept and verify some assumptions. But of course, we cannot replace an experiment in orbit, and this is the main objective of the ULEAD mission. So what is needed exactly to demonstrate? Well, we need to evidence some critical system level capabilities. The first one being our capacity to use digitally recorded signals to compute visibilities as we are used to in SMOS data. This requires a very fine post-synchronization, that is, synchronize all the measured signals from different spacecraft down to a common time reference. This has been demonstrated on the ground through VLBI experiment and partially in orbit through space VLBI, but never before on a small scale satellites and for very close formation flying. This is the next challenge that we need to address in ULEAD. That is the short range autonomous formation flying. All these satellites will be operating at very close range, and it cannot be maintained from the ground, of course. So we need to design autonomous formation maintenance, and that will be operated on board. We also have a couple of secondary objectives. We want to demonstrate the radiometric accuracy enhancement that we can expect from using a slightly different way to compute visibilities, mainly using the subband processing instead of computing correlation and visibilities on the total waveband of the instrument. And also to enhance the radiometric accuracy by integrating, artificially expanding the integration time in the image space. One major improvement that we want to assess is, of course, the RFI mitigation for interferometry. This has been, as I said, demonstrated by SMAP for total power radiometer. It's slightly more complicated to deploy for an interferometer, and we want to be able to check exactly what can be done and with what performance we can expect. And also, we need to redesign, completely redesign our reconstruction paradigm, because SMOS 1 will not be applicable. From this, we derived some mission requirements for this demonstrator. We set up for 3 antennas on 3 different nanosatellites to construct long baselines between 30 and 50 meters, with an accuracy in the pointing no less of 0.05 degrees, and a detection capability in IQ and HV polarization covering the whole band. We also need to sample, of course, this L-band and lysis band, and also a shoulder band that we will be using for synchronization signal. To keep the onboard processing and computing power manageable, we limit ourselves to an acquisition span of 30 seconds at a time, and with minimum of 5 acquisitions a day. The quantification is done on A-bit to be able to compute correlation without degrading the performance of the instrument. And the relative positioning on the antennas afterwards through on-ground processing is aimed at determining the relative position of the antennas within with an accuracy of 3 millimeters. Equivalently, the relative datation, that is the synchronization of the signals, including the clock biases and drift, need to be achieved with a 10 picosecond accuracy. I will not linger too much on the synchronization. I invite you to attend the Eric Anterior presentation tomorrow afternoon, which is completely dedicated to this, because this is clearly one of the major challenges that ULEAD has to address. I will now move on to the flight dynamics of the mission.
Sorry, you have 2 minutes left.
Yeah, okay. So the SMOS orbit is used as reference, where the plane of the SMOS orbit has the 6 a.m., 6 p.m., and we selected the formation flying solution, which will have all 3 satellites rotate around a virtual chief, which is numbered 0 in the small animation you see on the right. And but which also minimize the collision risks if in the event of one of the satellites failing, and that would start to drift uncontrolled. Also, we had to select a lower altitude of 600 kilometers to comply with debris regulation without planning for added fuel requirements. So this the formation flying will be monitored on board, through, of course, each of the satellites will carry a GPS receiver, and they will exchange all their information of position, and each will have an autonomous capacity to compute the best solution for the navigation control. It's estimated that all variations need to be corrected daily through 3 maneuvers for each of the satellites. I will just make a short introduction on the acquisition and storage that we designed for ULEAD. So as I said, it will digitize the signal from 1400 to 1429 megahertz in IQ and 8-bit digitization. The front end is required to be quite performant, not to introduce a noise. And if we multiply on the bit rates and the number of channels and bits, you come up with a 960 megabits per second acquisition rate that we need to store in real time. So that will be done through basically after the front end, which is just 2 identical channels of LNA and filters, RF transceiver, which will assure the quantization of the signal and pre-processing, and Zinc, which will provide the interface to mass memory. The mass memory, which is constituted by 4 flash NAND, 4 gigabytes, yielding 45 megabytes per second per bank, so making it possible to store 30 seconds of acquisition in real time. Very short introduction on the on-ground processing that we envision. The most important are the first 2 steps, which is the calibration, the radiometric calibration, and especially the synchronization to a common time reference. This is instrumental to the success of the mission, of course. The RFI analysis, as I said, which is based on a time frequency analysis, and the filtering and the discarding of some samples before the computation of the correlation. Also, we plan to go up to the level 1 to the brightness temperature maps, even if the ULEAD-based brightness temperature maps will be probably very lousy because we have a deficit in frequency coverage. But we plan to enhance this by using SMOS historical data or simultaneously acquired SMOS data. The mission scenario is very rapidly. Just we select 5 acquisition zones. Of course, one is centered in Toulouse because this will host also the synchronization beacon that we will use for synchronizing of the data. And some various surfaces. One in China, which is yet to be determined exactly. This is obviously to challenge our RFI mitigation algorithm, and 2 specific targets for calibration. We also plan to have simultaneous acquisitions with SMOS, provided SMOS is still operating, of course. Every 8 days, we compute that we have a number of acquisition opportunities, and we select one to demonstrate our capacity to kind of enhance SMOS resolution.
Francois, I am afraid you have to go to the conclusion. Sorry.
This is the conclusion. So the status of the mission is this one. We completed the phase 1. Our final review was end of September. We are now moving on to complementary studies for specific technological issues, the inter-satellite link and the star tracker mainly, and also to complete the performance budget and end-to-end simulation to validate our processing algorithm and mainly the synchronization. Phase B will start early 2021, and the launch is expected mid-2023, with the mission lifetime expected to be for 1 year. And with this, I will stop.
Thank you, Francois, and sorry to interrupt you 2 times.
No problem.
So let's see if there are questions. Just one short question, if possible. Let me just wait a few seconds if there are questions coming from the chat. Okay, so if not, okay, I think we can move to the second part of this section, and we'll give the floor to the co-chair, Manuel Martin Neira. Manuel, please.
Thank you, Nazareno. Yes, let's move to the next presentation. It is about the new L-band passive radiometer for Earth science and applications, the ESMOS high resolution mission. And it will be presented by Nemesio Rodriguez Fernandez. Nemesio, the floor is yours.
Thank you, Manuel. So good afternoon, everyone. Manuel already introduced the title of this presentation. This is work done at CSVU in collaboration with other research laboratories in France, with SARSAT in Spain, and with CNES, and with Airbus Defence and Space. So the SMOS HR mission, the SMOS high resolution mission. First, just a few words about SMOS. Not much to say after the last presentations. 69 antennas in interferometric mode to synthesize an aperture of about 7.5 meters to get a resolution of 25 to 50 kilometers, depending on the position of the footprint within the field of view. You did know already that it performs full polarization and multi-angular acquisitions. Regarding the applications, they go well beyond the first variable, solid moisture and ocean salinity. It's now used by the ESA Climate Change Initiative for solid moisture, for salinity, where it is a building block, but also is used by the biomass CCI. Superit is assimilated operationally at ECWF. Jan already mentioned this. So a lot of applications, some of them definitely will need higher resolution. Maria Jose also discussed a lot of applications. We do understand that for melting events close to the coast in Antarctica, for hydrology, for agriculture, definitely if we have an instrument with higher resolution, it will be much better for those applications. Let me also just add that high resolution is also needed for ocean studies, which could look less evident for some people, but if we really want to understand the physics of these mesoscale processes linking physics and chemistry in the ocean, close to the coastal regions, for instance, in this example, by Nicolas Renardin, linking salinity and chlorophyll, we will need higher resolution. As an output of this community contributed the study of land, ocean, and cryosphere research and operational applications. The resolution of the future mission was studied, and you see displayed that the number of applications increased significantly when you go to resolution 10 kilometers as a breakthrough resolution or 1 kilometer as a final goal. So you might think, do we really need this? We do know already how to disaggregate SMOS data. So we ask ourselves this question as well. We took data from the NAFI campaign in Australia, some of the original data that were used to put in place the first disaggregation algorithms for SMOS using the dispatch method by Olivier Merlin. This 1 kilometer was aggregated to 5, 10, 20, 40 kilometers. We apply dispatch, we downscale to 1 kilometer, and we compare the results. So this is what you see in the scatter plots. And you will see that when you compare the disaggregated 1 kilometer maps with the original 1 kilometer maps, when you have a start at 40 kilometers, you will get a correlation of 0.63. If you started at 20 kilometers, 0.67, at 10 kilometers, 0.7, at 5 kilometers, 0.75. So the resolution definitely increased. The higher the initial resolution, the better the disaggregation results. Taking all this in mind, we started to think about new concepts, and we came out with the SMOS HR concept as an interferometer to get a resolution of around 10 kilometers on Earth. We shifted from hexagonal patterns as those used by SMOS to Cartesian grids. Why? Because actually, with these two configurations, an array with a square array or a cross with 4 arms array with 12-meter arms, we do get the same resolution. They are basically equivalent, and don't miss the next presentation by Eric Anterior, who will give you a lot of more examples of this. But we can implement a new method to increase the density of the sampling of the Fourier plane. This method has been patented, and basically is that once you realize that the fourth arm is in principle redundant, you can play around with antennas in this arm, shift them a little bit in both directions by basically half of the step, and you are getting the UV coverage that you get in the bottom of this figure. All the red points are coming to densify the Fourier plane. So, of course, this reduces the aliasing in reconstructed images. Airbus studied these two architectures. They managed to find out how to deploy both of them. For the cross, it kind of looks obvious. It's not the case for the square, but it's possible. At the end of this phase 0 study, the cross configuration is preferred because it's a simpler architecture and it shows lower risk. It can be tested at zero gravity before launch. If there's a problem with the segment during the deployment, the instrument will remain in operation, which is more difficult in the case of a closed geometry as a square. Those images in the top left show you the major and minor axis of the footprint ellipses within the field of view, the alias-free field of view. You will see that basically you have 10 to 15 kilometers everywhere within the field of view. You can compare with an equivalent figure on your right by SMOS with resolutions from 27 times 27 to 35 times 56 in the outer part of the field of view. And in the bottom images, you have examples of the simple simulations with a constant brightness temperature for the Earth and a constant brightness temperature for the ocean, reconstructed with SMOS and reconstructed with SMOS HR. You see the effects of the increased resolution in the border in the transition regions from the ocean to the land. So once again, there is the next presentation discussing more details. So RFI, of course we have to deal with RFI. RFI is not something exclusively related to L-band, as you know, but we have to deal with this as well. SMAP could do it in an efficient way using the experience by SMOS, and SMOS HR, of course, will have advanced RFI mitigation. Our colleagues from Airbus have been working on this to put in place new algorithms to mitigate, to filter out multiple narrowband RFIs and also wideband modulated RFIs using a combination of different techniques. I would like to move to polarimetry and signal quantization. First, let me remind you that SMOS cannot measure simultaneously both polarizations. In one integration time, you observe one polarization, in the next one, a mix of polarizations. The other one, visibilities for XY. The third one, you get Y, and the fourth one, XY. Of course, the radiometric sensitivity depends a lot if you have a pure, let's say, X polarization snapshot or a mixed one. In contrast, SMOS HR will observe simultaneously the two polarizations, so the acquisition of the scheme will be much simpler. You can understand very easily that it will make a much more efficient use of integration time, basically increasing the integration time for a given polarization of a factor of 4 over 1.3, decreasing the noise by a factor of 1.7 with respect to SMOS. Regarding the quantization, instead of 1 bit, SMOS HR will quantize signals using 8 bits with virtually no losses due to the correlation due to 1 bit quantization. This also will decrease the noise by a factor of 1.35. So, in this table, we summarize some of those characteristics. Let me just point out that antenna spacing can be larger than that of SMOS because this, due to this patented method, actually the density of the coverage of the Fourier plane is denser. So 1.7 lambda, even if the antennas are spaced by 1 lambda. I did mention the full polarization simultaneous acquisitions and the integration time, the quantization of the signals, both making use of much more efficient use of the integration time. So taking into account this, we do get a radiometric sensitivity similar to that of SMOS, because otherwise, of course, a bigger instrument, a bigger interferometer has a larger noise multiplication factor. Eric is mentioning this afterwards as well, I think. So the good point is that we have a much larger instrument with a much better resolution and still the same radiometric sensitivity as SMOS. And don't forget, of course, that for geophysical retrievals, we don't use just a single snapshot. All applications will use the signature of different...
Nemesio, 5 minutes to go.
Okay, thank you. As in the case of SMOS, it's an imaging instrument. In every footprint, you will get brightness temperatures for different incidence angles depending on the position in the field of view, and a consecutive snapshot will still observe most of those footprints with a slightly different incidence angles. So actually, the radiometric sensitivity for most geophysical applications will be much better than that of a single snapshot. What else? This has been shown already by Jan. So UNIT has also been presented just by François Cabot. Next step could be going to an instrument, to a concept that we call SMOS Next. We started the phase A at CNES a couple of months ago. It will be a central carrier similar to SMOS HR, surrounded by nanosatellites similar to those of to get resolutions around 4 kilometers. We are working on the mission specs of this mission now, in particular the number of nanosatellites, the positions, taking into account the constraints in the orbits, etc. This is an example of how the video coverage of the Fourier plane could look like for SMOS Next. As a summary, SMOS is 11 years old. It's working well, but the follow-up with at least the same characteristics, ideally much better resolution is needed. The SMOS HR concept finished the phase 0 study at CNES to get a 10 kilometers resolution with 230 antennas and arms of 12 meters. And SMOS Next is the following steps. The phase A study started a couple of months ago. It will be a central SMOS HR-like carrier surrounded by unit like nanosatellites. Thank you for your attention.
Thank you, Nemesio, for this interesting presentation. We have time for a couple of questions.
Can I just interrupt for a technical reminder? I see that there are some questions posed on chat, and in one case it was unanswered. So I would again encourage all the authors to try to put directly the question by switching on their microphones. That's all. Thank you.
Okay, yes, we have a question on the chat. Can you comment, Nemesio, on the specific RFI mitigation techniques that will be explored in this demonstrator mission? Oh, well, this is for François, sorry.
Yeah, François just answered in the chat. It's not so different. Right. Conceptually, it's not so different to methods used by SMAP or other published methods. Is the combination of those, in particular, what we are thinking for SMOS HR or next, is a combination of all those methods that are used in a smart way. We cannot mention much more because our colleagues from Airbus are putting some patents on this as well, but it will be definitely a very good improvement with respect to SMOS.
Okay, thank you. Thank you, Nemesio. Any other question from the audience? All right, if not, we move to the next presenter. It is Eric Anterieur, and he will be giving a talk on preliminary system studies for NESMOS high resolution for one mission. Eric.
Okay, thank you. Do you see my screen?
Yes.
Okay, thank you. So together with my co-authors, I will present here preliminary results of studies conducted for high-resolution SMOS follow-on mission. This work takes place in the long story of the global L-band measurement started by SMOS 11 years ago. The goal is the continuity of the L-band measurements while increasing the spatial resolution to about 10 kilometers without degrading the radiometric sensitivity and keeping the revisit time of 3 days unchanged. Accounting for the difficulty to deploy large real aperture in space and for the successful alternative approach used by SMOS, SMOS HR will also perform aperture synthesis from space. Geometries leading to Cartesian and to hexagonal sampling grids have been studied, and 4 types of arrays have been studied: cross and square-shaped array over Cartesian grids, Y and hexagon-shaped arrays over hexagonal grids. When these arrays are populated with equally spaced antennas with a spacing d along the arms, the baselines vectors and the corresponding Fourier frequencies belong to a grid with a sampling step d over lambda, except for the cross and square-shaped arrays, for which it is divided by the square root of 2. Thanks to this red arm that is translated with respect to its usual position. This design that leads to a smaller sampling step in the Fourier domain and therefore to a wider field of view with less aliasing, as reminded by Nemesio, this design has been patented. However, no evident solution has been found for generalizing this property to Y and to hexagon-shaped arrays. The distributions of this Fourier frequency, what we called the frequency coverage, are shown here with colors indicating the level of redundancy of the corresponding baselines or Fourier frequencies. Coming back to the arrays, those ones cannot be calibrated with the head of the well-known redundant spacing calibration approach. Almost one additional antenna, shown here in green, is needed for these arrays to be full phase one, and more than a single one if these arrays have to face potential failures in the calibrations. Coming back to our study, few parameters have to be optimized with the objective of satisfying scientific requirements. This is a case of the shape and of the extent of the field of view, which depends on the geometry of the array, on the spacing between the antennas, and on the orientation of the platform. This is also the case of the angular resolution and of the radiometric sensitivity, for which the total number of antennas plays a key role. Here are a few examples of the synthesized field of view with arrays leading to Cartesian grids on the left and to hexagonal ones on the center and the right. The spacing there has been set to values for which the sky aliases of the Earth one, in brown, are sticking to one another. These are just illustrative values, but we can clearly see the different shapes of the alias-free regions. The spacing between the antenna is here fixed to the same value, and we can see the impact of the platform tilt angle. On the top, the platforms are looking in the nadir direction, and on the bottom, they are looking into a direction tilted 20 degrees from the nadir. Here, the situation is the opposite one. The tilt angle is set to 15 degrees, but the spacing between the antennas is shorter on the top than on the bottom. Consequently, the extent of the alias-free field of view is larger on the top, and the range of ground incidence angles is also wider. Here it is summarized the impact of the spacing and the tilt angle on the alias-free swath on the top and on the revisit time on the bottom, with a white line showing the 3 days revisit time, which is the target. Here is illustrated the impact of the same parameters, but on the range of ground incidence angles. Depending on the orientation of the platform, the nadir-looking direction, here in green, might be in a region free from any alias, in the Earth alias-free region, or on the border. Here it is for a cross and for a square shape array. Here it is for a triangle or an hexagon shape array. Here the same, but with the same orientation as SMOS. And here is the well-known case of SMOS with this direction in the only Earth alias-free field of view. Coming back to the arrays and to the very principle of aperture synthesis, the collecting area is proportional to the total number of antennas and to their diameters, which cannot exceed the spacing between the antennas. Regarding the angular resolution, it is driven by the frequency coverage, both in shape and in extent aspects. Here, as an example, the number of antennas is chosen in such a way that the solutions are sharing the same disk inscribed in the frequency coverage. We can clearly see differences with regards to the circumscribed disk in terms of diameter and extension of the empty areas without any Fourier frequency. When accounting for this property, a ground resolution of 10 km is not a dream. The next slides aim at presenting preliminary results for two candidate arrays more carefully studied. The target is 3 days revisit time. As a consequence, the shortest spacing is set to lambda over the square root of 2, but the spacing between the antennas along the arm is equal to lambda. As the target is 10 km for the ground resolution, both are equipped with 231 antennas. As a consequence, the size of the imaging matrices is of course much larger than for SMOS. Although these matrices are bigger, they are still invertible. This is shown here with the singular value decomposition. It has also been necessary to pay attention to the number of operations performed during the inversion. It is shown here that the propagation of round-off errors has no impact on the solution. With regards to the inversion of complex visibilities, the methods implemented for SMOS have been studied with the objective to check if the behavior is the expected one. Here, for both arrays, the cross on the left, the square on the right, are the brightness temperature retrieved from complex visibilities when observing a flat Earth at 100 K. Visibilities have been blurred by an additive Gaussian noise with standard deviation 0.10 Kelvin. The average seen after 1,000 random trials are shown together with the histograms of the TB in the alias-free region in blue and in the Earth-only alias-free region in brown. The spatial distribution of the standard deviation are shown here. Although we are not in a situation that allows to identify these figures to the radiometric sensitivity map, these simulations show clearly the propagation of noise from visibilities to retrieve TB. Here at both sites, the amplification factor is 68. Here we remind of the same number for SMOS. The amplification factor is only 25. This difference is expected, but here, when accounting for the improvement that will benefit to SMOS HR compared to SMOS, the situation is not as dramatic as it could be at the first glance. The same exercise has been performed for a Fresnel SEN to check the behavior of the differential inversion approach compared to the standard one. The improvement is clear, and the conclusion is that the differential approach behaves exactly like it does with SMOS. This is also true at the level of the profiles for the brightness temperature in H and V polarization. To conclude, we have presented preliminary results of studies conducted for high-resolution SMOS follow-on mission. The goal of this mission is to ensure the continuity of L-band measurement while increasing the spatial resolution up to 10 km without degrading the radiometric sensitivity and keeping the revisit time of 3 days unchanged. 2 candidate arrays have been selected, and there are still ongoing studies. Thank you very much.
Thank you, Eric. Thank you very much for your presentation. The floor is open for questions.
Good afternoon, everybody. It's Giuseppe Virone, CNR. I have a quite a maybe generic question to the SMOS community, and of course, in particular with this talk. And the question is it possible, I mean, using the SMOS radiometer architecture to start thinking about higher frequencies? I mean, is there do you already have an idea about the technological limitation to extend this kind of radiometer to higher frequencies?
Probably I am not the person with the best place to answer to this question, because technological aspects are not in my field of experience. I'm sorry.
Yes, maybe I can say something. There have been studies to build wave interferometers from geostationary orbit in the compound of oxygen around 50 GHz and in the resonance of water vapor at 183 GHz. So yes, there have been studies for high frequency interferometers in this particular case where the target of the Earth is stationary with respect to the interferometer. Maybe somebody else from the audience can add something to my answer.
Jan speaking, if I may say something on this. Yes, there were other studies on this. And at higher frequencies, typically X band, some at C band, and some at Ka band. It's feasible. It's more challenging technologically speaking for the dimensioning of the antennas and their positioning, and also in the stability of the instrument. But as you need smaller arms, it's also less stringent on that part. So it's something studied and feasible, but there are still a few challenges.
Yes. Any other question to Eric on his presentation?
Manuel, Niels Skov here.
Yes, go ahead.
Things have not only been studied, but Altana JPL has actually made demonstration models and bits and pieces of such a system at the high frequencies, and also a demonstration model has been operated from the roof of their building. So work has been done, that's absolutely sure.
Yes. Thank you, Niels. Any question to Eric?
Hi, Manuel. This is Joel. I was wondering,
Hi, Joel.
Eric, if you showed some simulations of targets that were pretty uniform spatially. I wonder if you've done any simulations for non-uniform targets spatially to try and show the resolution in a simulation.
Yes,
Okay.
yes, we did, and in fact, in the presentation of Nemesio, you saw simulation over Spain, if I remember well.
Okay, thanks.
Any other question to Eric? So, Eric, I have a question from my side. So, you have this square array, and you managed to reduce the aliasing effects by one side at a slightly different spacing with respect to the other three sides. Is this correct?
Yes.
Yep. Very well.
It's a very nice property of Cartesian grids, but we do not succeed in finding the same properties over hexagonal grids.
Yeah. It was clear, yeah. Thank you, Eric.
Thank you very much.
Yep. If there are no any other question, then we move to next speaker. That is Eugen Rashinov. And Eugen will be speaking spaceborne experiment convergence, the vertical profile of atmospheric humidity retrieving by passive microwave methods. So Eugen, if you can share your screen, please.
I did.
Yeah, good, fantastic.
Hello, my name is Eugen. I am a graduate student of the Space Research Institute, Russian Academy of Science, and I will present you a report on the topic presented on the slide. Spaceborne experiment convergence will be carried out on the Russian segment of the International Space Station. During the experiment, it is planned to measure the absolute radio brightness temperatures of the ocean atmosphere system of tropics in the range of 10.6 to 200 gigahertz to retrieve detailed atmospheric temperature and humidity profiles and to investigate thunderstorm activity. The main scientific instrument of the experiment is scanning microwave radiometer spectrometer MIRS, which is designed to measure the radiothermal radiation of the Earth in the microwave range. It is multi-channel radiometer that has conical scanning. One of his priority tasks is to retrieve the profiles of the absolute atmospheric humidity up to heights of 12 kilometers at 8 or 10 levels. The MIRS radiometer has 22 frequency radiometric channels, 7 of which are located near 183 gigahertz water vapor absorption line and designed for the atmospheric humidity profiling. Our investigations show that additional use of frequency channels near the weak absorption line of water vapor of 22 gigahertz can improve the accuracy of humidity retrieving in the lower troposphere. Therefore, channels from 24 to 26.5 gigahertz have been added to the traditional channel set. Retrieving of temperature profiles will based on measurements in the 60 gigahertz oxygen absorption band. The main task of this work is the preparation of techniques and software for the operational processing of the expected data of the new space experiment convergence, and the assessment of the expected errors in the atmospheric humidity profile retrieving. The humidity channels of the MIRS instrument are selected in such a way that they are sensitive to changes in atmospheric humidity up to heights of about 10 or 12 kilometers. The corresponding functions of sensitivity are shown on this slide. It can be seen that these functions are wide enough and overlap each other, which makes it difficult to solve an already complex inverse problem. The dotted line shows that weighting function that can be obtained from a set of new channels near to 22 gigahertz. They have good sensitivity to humidity from 1 to 4 kilometers. We have performed a simulation of the radiometric data of the MIRS instrument. Simulations were carried out using the Rosenkranz radiative transfer model for the atmosphere and the Meissner-Vance model for the raw ocean phase. On ECMWF interim reanalysis was used as source of meteorological data for simulation. It containing global fields of the meteorological parameters with a resolution of 0.125 degrees. For the convenience of modeling, the parameter fields were taken at 12 hours for 1 day. Further, the scanning geometry of the MIRS instrument was calculated, taking into account the parameters of the ISS orbit. The brightness temperatures were spoiled with Gaussian noise in accordance with the sensitivity of the radiometric channels. As a result, the global fields of simulated temperatures of the MIRS instrument were obtained on all channels for the ascending and descending orbits of the ISS. It contains about 1.5 million of data points. An example of simulated field of brightness temperature is shown on this slide. To solve the inverse problem, the artificial neural networks was chosen. Since it is effective in solving non-linear inverse problems using noisy signals. The most common neural network topology is a feed-forward scheme in which information transmits from input neurons through one or more hidden layers to one output layer. A mathematical model of a neuron is shown. Each neuron has a set of weights and an activation function. We use a network with one hidden layer with a sigmoid activation function. It allows us to take into account the nonlinearity of the problem. The optimal number of neurons is determined experimentally. The figure shows the dependence of the retrieving error on the number of neurons. It can be seen that after 100 neurons, the error falls slightly. So 100 neurons were used in the hidden layer. An important part of the neural network algorithm development is the creation of training and test samples. The samples were formed from previously simulated data. We used 100,000 randomly selected points as a training sample, and the rest, 1.4 million points, was a test sample. The slide shows that spatial distribution of the samples. The red dots indicate the points of the training sample, and the gray dots are the test sample. And you can also see the statistical characteristics of the two samples. It can be seen that they are very close. During the work, we investigated which input data for the neural network gives the smallest retrieving error, and how much is influence of the expected instrumental noise on retrieving error. Each time a new network was trained with the same topology. The estimation of the retrieving error was carried out according to the formula presented on the slide. At the first stage, we investigated the quality of retrieving in the absence of the instrumental noise. Brightness temperatures of the 183 GHz channels only and the 100 GHz channels together with 22 GHz sent as input for neural network. It can be seen from the figures that use of channels in the 22 GHz region in the absence of noise leads to a decrease the retrieving error by almost a third. However, the error rate remains quite high. We assume that a large retrieving error under ideal conditions may be caused by the lack of information about atmospheric temperature profile. This assumption was tested by additional sending the profile of the precisely known thermodynamic temperature of the atmosphere to the network input, together with a set of brightness temperature of the MIRS humidity channels. It can be seen from the figures that the retrieving error decreases significantly in this case. Complex profiles with inversions are retrieved almost exactly. It also can be seen that the use of frequencies near 22 GHz reduces the retrieving error in the lower troposphere. As a result, it can be concluded.
Again, 5 minutes left.
As a result, it can be concluded that the optimal set of input data from for the neural network algorithm are the brightness temperatures of the humidity channels 183 GHz and the 22 GHz and the atmospheric temperature profile. The MIRS instrument made to retrieve the atmospheric temperature profile up to 15 kilometers. For this task, 6 channels in the oxygen absorption band from 50 to 70 GHz are used. The modeling showed that the retrieving of the atmospheric temperature profile may be performed with a mean square error about of 1.5 Kelvin, which is the level of world analog. For example, on the slide shown the retrieved temperature profiles for the investigated model sample. The last stage of the work is the assessment of the influence of instrumental noise and errors of the temperature profile on the results of retrieving the humidity profile. For this, the brightness temperatures were spotted with Gaussian noise, and then the temperature profile was retrieved. A new neural network presented on the slide was compiled, and the resulting errors in retrieving the humidity profile are presented on the slide. As you can see, instrumental noise has a strong effect on the retrieving error. It almost doubles the error. Also, it can be noted that the use of additional radiometric channels in the 22 gigahertz region leads to a decrease in the retrieving error in the atmospheric layers from 1 to 4.5 kilometers. The presented errors in retrieving the humidity profile can be considered final for this work. On this slide, you can see the main results of the work. A neural network algorithm that allows to retrieve humidity profiles of the atmosphere during convergence experiment was developed. It is shown that the best results in humidity profile retrieving may be obtained with taking into account the temperature profile. It is shown that the additional use of channels near the 22 gigahertz water vapor absorption line makes it possible to reduce the retrieving error of the humidity profile at heights from 1 to 4.5 kilometers. Thank you for attention.
Thank you very much, Eugen. So, if there are any questions for Eugen, go ahead.
I have one question.
Please.
Possible. Yes, is on the setup of the neural network architecture, because I see that you used a very large number of neurons and a so complex architecture in general. It's true that the cause of decrease of the retrieval error, but also it increases the risk of overfitting. How did you manage the overfitting in this case? I mean, with overfitting, the network is overtrained on the given training set, so it's able to reproduce very well the training set. But since it also fits the noise in the data, the risk is to have completely failed the test set by using different kind of data. And how did you address this point, this very important point for neural networks?
We prevented overfitting of the network by dividing the training set to the 4 group, and training performed due to error of the retrieving error of the retrieving should be lower in the all of these 4 groups in testing sample.
Okay. Okay, thank you.
Is there any last question for Eugen?
I have a question. This is Nico Cimini, if I may.
Yes.
I'm wondering what's the field of view of the different channels, and if that was considered in the simulations for the neural network retrieval training. Thanks.
No, we in our simulations we used infinite tiny field of view of the radiometers.
Okay, thanks.
Thank you again. We move to the last presentation of this session. It will be given by Alexei Kuzmin. It is titled Microwave Radiometer Spectrometer, the Space Experiment Convergence. Alexei, please, if you can share your screen, please.
Yeah, hello.
Yes, thank you. Go ahead.
Hello, dear colleagues. I welcome you. I hope that you can hear and see me well, and this new conference format will not interfere with our fruitful communication. My name is Ilyas Sadovsky, and I represent a scientific group from the Space Research Institute of the Russian Academy of Sciences. The topic of our presentation you can see on this slide. The main focus of our department is the study of the microwave radiation of the ocean atmosphere system. This includes laboratory and field experiments in which we obtain data for refinement and develop theoretical radiation models of this system. In addition, we are engaged in design and manufacture of microwave radiometers for scientific application. Also, part of our team is engaged in the processing of satellite radiometric information to study such natural phenomena as tropical cyclones. While working on the last of the listed tasks, we encountered a number of problems. Among them, in recent years, due to the current political situation, informational exchange in the field of satellite radiometry has become difficult. Among more than 13 operating satellite instruments, only one is Russian, to which we have an unlimited access, MTVZA-GIA. This is clearly not enough. Qualitative information from MTVZA-GIA began to arrive only this year. The scanning parameters of MTVZA-GIA differ from similar instruments, which makes it difficult to combine this data. Insufficient spatial resolution of existing systems does not allow to a detailed analysis of cyclonic activity. Considering the above, our team came up with a proposal to create another Russian instrument focused primarily on studying the state of atmosphere in cyclones areas in points of their origin and disappearance. This initiative was supported by the Russian Academy of Sciences and the government of the Russian Federation. Thanks to this, in 2018, the Space Experiment Convergence has begun started, which is planned to be implemented on board the International Space Station. To implement this experiment, a microwave radiometer spectrometer MIRS is being developed. Several Russian organizations working in the field of space instrumentation are participating in this project. Some of them are presented on this slide. It should be noted that all the results that I will talk about in my speech are only the results of design and modeling. To date, not even a maquette of this device has been created. But already now, based on the results of modeling and achieved characteristics of separated units prototypes, it has been shown that instrument with the declared characteristics can be created and will be able to function in space on board the International Space Station. Simulation of MIRS data, taking into account all parameters and noises, demonstrate that all tasks of the space experiment can be solved. So, MIRS. The appearance of the device is shown on this slide. Here, a standard configuration for such system is used. Similar configuration is used, for example, in such devices as SSMIS and MTVZA-GIA. The main components of the system are shown on this slide. The preliminary dimensions of this system you can see there, and the weight of the device is about 50 kilo, and the power consumption is 100 watt. The MIRS antenna unit rotates relative to a fixed base. This provides a consistent view of the surface and the atmosphere about it as the International Space Station moves. Earth incident angle lies in the range from 50 to 57 degrees. The specific value depends on the frequency channel. The rotation period is 1.3 seconds. For the International Space Station orbital altitude, which is about 400 kilometers, the swath width is 800 kilometers. It is important that we have two working areas of observation. in and against the direction of the International Space Station, each one for 120 degrees. That is, each surface element is observed twice, and this is a necessary condition for the near-surface wind vector retrieval. The diameter of the main reflector aperture is 700 millimeters. As irradiators, and there are 9 of them, according to the number of the radiometers, Pottern horns is used. Since irradiators are spaced apart, we get a composite radiation pattern. The location of the corresponding elements on the surface is shown on this slide. The list of frequency channel and their characteristics is shown on this slide. As mentioned earlier, this combination is achieved through 9 radiometers. Different radiometers marked with different colors. It can be seen that some of them operate in several frequency ranges, and some of them operate at 4 linear polarizations. All radiometers are built according to the full power scheme due to the very short signal accumulation time per each resolution element. It should be noted that for detailed determination of atmospheric parameters, it is proposed to use a new set of frequency channels. Using of so-called difference measurements makes it possible to increase the accuracy of determining atmospheric parameters even in the lowest near-surface layers. A presentation describing this method you have already heard. MIRS uses a standard 2-point calibration. For this purpose, a cold space mirror with a 350 millimeters aperture size and a hot load with a temperature from 78 to 340 Kelvin are used. Calibration is performed in non-walking scan sectors for each rotation. The hot load is made from monocrystal silicon and looks like a set of pyramid with a height of 70 millimeters. This slide shows the approximate MIRS location on the Russian segment of the International Space Station. You can see the MIRS view sectors and interfering structural elements. In any case, the final location will be determined based on the actual design of the Russian segment at the time of the project launch. We plan that MIRS will solve the following tasks. At the end of my speech, I would like to present the results of simulation of the final data, which are planned to be obtained using 1 day of MIRS functioning, such as 10 meters surface wind speed, atmospheric water vapor, cloud liquid water, and vertical profile of atmospheric humidity and temperature. In conclusion, I would like to say that we hope that the project will develop. The launch of MIRS will allow testing all technological solutions and data processing techniques and will be a good addition to the existing space-based radiometric systems. Thank you for your attention.
Thank you, Ilya. I thought someone else was presenting instead of you. Thank you very much for this interesting presentation. Is there any question for Ilya? Ilya, I have a question. This MIR instrument on board the International Space Station, what is the status, the real status of this program?
Sorry, I don't hear you. Can you repeat, please?
Yes. What is the status of your program to fly MIRS on board the International Space Station? Is something already approved? Is something that needs approval?
It's just a beginning. So we, as you can see on the on this presentation, some of the elements are designed well, like this. So we have a prototype of these devices, but we didn't make a maquette of all the device. So it is a larger work.
Okay, but do you target some time frame where you could have in this program with an engineering model working in the laboratory?
We are planned that this device will be created in 2023 or maybe 2024. I think that.
Okay. Is that compatible with the lifetime of the International Space Station? I'm not sure how.
Yeah.
Yeah.
I see. No, we.
Go ahead.
I don't know how long the International Space Station will be operated, and you don't know too.
No, I don't know. I don't know. Okay. I see the frequency channels of your MIRS instrument are the same or similar or included in the channel set of ISRA's method of second generation. So maybe if data from the method of second generation satellite are available, you could perhaps test your retrieval algorithms with those data.
Oh yes, we try to build our method and algorithm according to the SSMIS data. So I think it will be possible to use it for MIRS.
Yeah. Very well. So this concludes the session. Just wanted to tell some authors like Eugene and Eric that you have questions in the chat. Please check the chat questions. And otherwise, on behalf of my co-chairman, Nazareno, we thank all the presenters of this session and give the floor to Emmanuel or Marco.
Okay. Thank you, Manuel. Thank you, Mauro, and thank you to the participant to this session. Now, we have the break for a virtual coffee, and this is again for the presenters for the next session. Please do not forget to join the pre-session that will start in a few, almost immediately. For checking the audio, video, and screen sharing function to ensure all will run smoothly also in the next session. I see that the authors are replying on chat to the question that are still pending, so that's good. And that's all from my side too. See you in half an hour with the second part of the mission session.
Hi, everyone. Bye.
Bye.
Bye-bye. Thank you all.
Thank you. Bye.
Hi, Frank. How are you? You're muted. You're muted.
Yeah, now you hear me, right?
Okay. Hi, how
So,
are you?
quite well. You?
Good. Okay, okay.
Home?
Yes.
Yes, of course.
Do we have any choice?
Yeah. Well, actually, here in Rome, you know, that's because we don't have a complete lockdown.
Oh, really? Okay.
Yeah, but actually, we are trying to avoid
Yeah.
to be out, you know, as much as possible, of course.
Yeah, sure.
So
Sure.
we'll see next days. Okay, so we may try to see if we can switch, you know, at since there are 6 presentations. So do you want to make the first part, the second part?
Actually, I don't even know where the people are from. Lise, I know because I see her.
Yeah. Okay.
Yeah.
Do you hear me, Catherine?
Yes, I hear you.
Yeah.
It
I hear
works.
you. Hi, Lisa.
Hi, Prince.
And actually, Mario Papa is from our group as well. I mean, the kind of.
Okay, so maybe you can present the 3 last ones and I do the first ones.
Or we can switch if you want, if you don't want to present Lisa.
It's not a problem. You can do it. I mean, just let me know.
Yeah, it's the same for me. Okay, Marian, we know him. And then, I don't know, actually.
Hello everyone. Hello, Frank.
Hi.
I'm Francesco. I'm the session manager for this session.
Oh, hi, Francesco.
I would like to first test the audio and the share screen of every of the presenters.
Okay.
Perfect.
Okay. So, Liz Kilic, can you hear me?
Yes.
Okay. So let's try to. Okay. You are the presenter. So let's try to share your screen and your video.
Okay.
All right.
Okay, you can see the presentation.
Yeah, it works pretty fine.
Okay.
Thank you.
Hello, everyone. Hello, Frank. Hello, Catherine. Hello, Francesco.
Hello.
Hi.
Hi, I'm Mark. How are you?
Hi, Mark.
Just wanted to test my audio and video.
Yeah, I will let you. Have the privilege to do this. Okay. Yeah, you can.
Okay, so I'm just gonna share my screen here. Can you see my screen?
Yeah.
Can you see me switching through the slides?
Yeah, very well.
Perfect.
Also the audio is nice.
Perfect. Thanks a lot.
Thank you. Joel, are you hearing me?
Can you hear me?
Yeah.
Okay.
So I will let you try to share your screen. So.
Yep.
Okay.
How's it look?
Yeah. Very, very well.
Okay. Thank you.
Thank you, Joel. So Mario Papa.
Hello to everyone.
Okay. Yeah. Try
La
to
risoluzione di SMAP.
try to share your screen.
Okay.
Yeah, we are waiting. Yeah. Now it appeared. Yeah.
Yeah. Okay.
Yeah, it seems pretty fine. All right. Also, the audio is nice. Thank you.
Okay, perfect. You're welcome.
So next one is Marian Klein.
Yes. Can you guys hear me?
Yes.
Very
Hi,
good.
Marian.
Hello, Frank. How are you?
Well,
Let me share
thanks.
my screen.
We don't see it yet.
Okay.
Yeah. Now
How
we
about
can
now?
see it.
Can you see it now?
Yes. Yes.
Okay.
Very nice.
Now you can see the talk coming, right? All right.
Yeah. It's fine. Thank you. So the last one is Tito Lupi. Tito, are you hearing me?
Yes. Hello.
All right.
Good afternoon.
So I give you the privilege
Okay.
to share the screen.
Yes. Okay, is it okay?
Yeah. Yes, it's fine.
Fine. The volume is okay for the microphone?
Yeah. It's good.
Okay, thank you.
Thank you.
Frank, can you answer to me in the chat, please?
Sorry, do you hear me, Catherine?
Yes.
Yeah, I would perfectly agree.
Okay, so I start or you start?
That's the same for me.
Okay, okay,
for you.
okay. I can start, and then you present the three last ones. Okay.
Great. Yeah.
Perfect. So
Okay, shall we have a kind of a ring or something like that, or just say 2 minutes left or something?
yes, that was my my questions in the chat. So I think that after 10, 12 minutes, we should mention.
Yeah, I think probably at 10 we can say 2 minutes left.
Okay.
And then stop it. Yeah, try to conclude at 12 and leave for the questions, right?
Okay, perfect.
Okay.
Sounds good to me.
Thanks a lot. So you can open and I can conclude so that.
Okay.
Implemented WordPress page.
Okay. Dear Catherine and dear Frank, I think we can start now.
Okay.
Let me do again my annoying recommendation very, very shortly. Please keep the schedule, 10 minutes for presentation plus 5 minutes for question and answer. And I would also remind to all the participants on WebEx that they now can unmute their microphones by themselves to ask a question, and that we will try to do our best to report the question from the YouTube chat. There is some delay between WebEx and YouTube, so possibly we will lose some question in case, but we will try again to do our best. And that's all. I will now leave the floor to Catherine and Frank, and thank you.
Excuse me, just a question. How can we have access to the YouTube questions? I don't know how to do that.
Yes, we will, Francesco and I will try to report the question from one to another, because it's not straightforward to follow the question by voice, the chat on WebEx, the chat on YouTube. So we will have in charge to forward in case the question from YouTube.
We don't have to check.
So just only have a look to the chat on WebEx, and in case we will report the question from YouTube to WebEx.
Okay, sounds good. Thank you very much.
Thank you.
Welcome.
Okay, so welcome to the last part of this current and future mission session. I am Catherine Pridgeon from Paris Observatory, and I will chair the first part of this session, and Frank Marzano will chair the second part of it. In this session, we will cover a very wide range of passive microwave instrumentation, from very low frequencies to very high frequencies. And we will also hear about diverse applications that will be discussed. We are almost 60 people right now on this session, so this is great. So after 10 minutes, I will let the presenter know that it's more or less time to conclude, and that we'll have 5 minutes for discussion. So you heard already about the way you can send questions. So the first presenter will be Lise Kilik, and we will start with polar applications with Lise. So Lise, can you share your screen?
Yes.
Perfect.
Okay, so everybody can hear me and see my screen?
Sounds very good.
Okay, so good afternoon, everybody. I'm Lise Kilik, and I will present you the ocean and sea ice algorithm developments for the Copernicus Imaging Microwave Radiometer, CIMR. So CIMR is a high-priority candidate mission within the European Copernicus Expansion Program. It is designed to observe the ocean and sea ice, especially in polar regions, with channels from 1.4 to 36 GHz with full polarization. Preparation for CIMR involves the development of innovative algorithms to maximize the benefit of the large spectral coverage and the high resolution of CIMR. Here we present an optimal estimation framework to estimate ocean and sea ice parameters, such as the sea surface temperature, the ocean wind speed, the sea surface salinity, and the sea ice concentration. This requires a careful analysis of the forward modeling of ocean and sea ice. So first I will talk about the developments for the ocean retrieval. Temperature, ocean wind speed, and salinity are key parameters for the ocean. To retrieve these parameters, inversion methods using optimal estimation are well known. To perform the inversion, a forward model is needed. For the estimation of sea surface parameters, different ocean radiative transfer models, RTMs, exist. Usually, these RTMs are developed or adapted for a specific application, for example, an instrument, a range of frequency, or incidence angle. And we need a model which is well suited for simmer. So 3 ocean radiative transfer models have been evaluated by comparison with SMAP and ABSOR2 observation. So we have in blue FASTEM, which is a fast parameterized model. In red, remote sensing system model, which is an empirical model fitting satellite observation. And in yellow, l'Océan, which is a physical model with parameters adjusted to L-band measurements. So first we can see the difference between the observation and the simulation for the different models. At 6.9 gigahertz, which is the key frequency for sea surface temperature. Then at 1.4 gigahertz, which is the key frequency for salinity. And at 36 gigahertz, which is a frequency sensitive to ocean wind speed. So we can see that major discrepancies were found at frequencies above 1.4 gigahertz for high wind speeds, as well as for cold temperatures. For now, the remote sensing system model is the most suited for to cover all the frequencies of simmer. So the simmer performances in terms of retrieval error have been evaluated, and a full simulator has been developed based on the remote sensing system model for the ocean and the Rosenkrantz model for the atmosphere. Ocean and surface atmospheric parameters are jointly retrieved by an optimal estimation algorithm able to exploit the simmer multi-frequency information. So here we can see the sea surface temperature retrieval error in blue for simmer and in yellow for the combination of SMAP and ABSOR2. And here we have a North Atlantic situation, so which represents the retrieval error for sea surface temperature with simmer and with ABSOR2. So this illustrates the challenges of retrieving the sea surface temperature in polar environments. For sea surface temperature, the performance analysis confirms that the defined precision requirement of 0.2 Kelvin globally and 0.3 Kelvin in polar regions can be met. The same analysis is done for the sea surface salinity. So in blue we have the simmer salinity retrieval error, and in yellow the SMAP and ABSOR2 salinity retrieval error. And we can see that the performance analysis confirms that the defined precision requirements of less than 0.3 PSU over monthly timescale can be met with simmer. Then it has been shown that there are discrepancies in the current radiative transfer models for cold temperature and high ocean wind speed. So an international team has been formed to work on the development of a new physically based ocean emissivity model. The aim is to refine current RTMs and provide a reference quality model for ocean surface emissivity that is consistent from microwave to the infrared. Then I will talk about the developments for the sea ice retrieval with simmer. So the sea ice concentration is a key variable to be estimated with simmer for operational navigation and climate observation. Passive microwave sensors can observe the sea ice concentration during night and through the clouds, but up to now they are limited in terms of spatial resolution. The existing algorithms are limited to the use of the 18 and 36 GHz channel, although it has been demonstrated that algorithms using the 6 GHz channel have the lowest errors. So here we present a new CIS concentration algorithm called the ice concentration retrieval from the analysis of microwaves, ICRIM, which is designed to fully exploit the simmer frequency and spatial resolution. The ICRIM algorithm is based on the optimal estimation machine to be consistent with the ocean retrieval parameters seen previously. So the forward model is a relationship between the ocean brightness temperatures and the CIS brightness temperatures, which are computed from the ESA CIS round-robin data package. Different channels combination to retrieve the CIS concentration have been tested. And the 6 plus 10 GHz combination shows the lowest error, but with a lower spatial resolution of around 15 km with simmer. And the 18 plus 36 GHz combination shows the best spatial resolution of around 5 km with simmer, but with a larger CIS concentration error. So what we want is to combine these two. So the seek retrieval is performed using the low frequency first at the low resolution, and then using the high frequencies at high resolution. Then the CIS concentration estimation at low resolution are combined with the estimation at high resolution using a data fusion method to obtain our final CIS concentration ice cream at the high resolution. So the resulting ice cream algorithm combines the benefits of the high accuracy of the low frequencies and of the high resolution of the high frequencies. Then we can apply ice cream using answer-to observation, and the results are compared to MODIS and OSISAF CIS concentration. So here we have the MODIS CIS, then the CIS concentration we retrieve with the ice cream method using answer-to observation. And here the CIS concentration from the OSISAF using answer-to observation. Several algorithm options are tested, and the study case shows that both high spatial resolution and good accuracy are obtained with the ice cream method. Ice cream has also been tested globally and for different seasons. Ice cream is globally applicable without fine-tuning or further filtering, except for coastal filtering, and the systematic use of fold channels from 6 to 36 GHz makes it robust to changes in ice surface condition and to weather interaction. So here we can see the retrieval with the 6 and 10 GHz, then with the 18 and 36 GHz. The combination of the two, which is the ice cream retrieval, and here the result from the CIS of the OSISAF. In conclusion, for the ocean, different ocean radiative transfer models have been evaluated with observation. Discrepancies appear for the cold temperature and high ocean wind speed. Simmer performances have been evaluated with the remote sensing system model. Simmer will provide sea surface temperature, ocean wind speed, and sea surface salinity, respectively, with a spatial resolution of 15, 15, and less than 60 kilometers, and a theoretical precision of 0.3 Kelvin, 0.4 meter per second, and 0.3 PSU, respectively. a reference quality ocean emissivity model from microwave to the infrared is under development. Then for the sea ice, the ice cream algorithm has been developed. It follows the optimal estimation that allows the using multiple channel combination to retrieve the sea ice concentration. A data fusion method is developed to combine the accurate estimate of the 6 plus 10 GHz channel with the high resolution estimate of the 18 plus 46 GHz channel. Our ice cream sea ice concentration estimates are very encouraging, providing both low errors related to the low frequency observation and the high spatial resolution obtained from the high frequencies. Simmer will provide the sea ice concentration with a spatial resolution of less than 5 kilometers and a theoretical precision of less than 5%. So here are the different references, and thank you for your attention.
Thank you very much, Lise. And this is well in time, so that's perfect. So any question? I can see one question on the chat. The question is not clear why sea surface salinity improves with respect to SMOS. Could you provide comments?
So first, Simmer exploits. Okay, maybe I can show this figure. Simmer exploits all the frequencies. So when you retrieve the salinity, the information provided with the other channels will give you information on the surface temperature that will help the retrieval of the salinity. And then we have noise that are lower than with SMOS, with Simmer.
Thank you. Perfect. Any other question from the audience? From the YouTube questions, any question?
No, we don't have any question from me.
Okay, perfect. So we can move to the next talk from Mark Lusner, which is about orbit design for satellite interferometry radiometers for super resolution Earth observation. So Mark, can you share your screen?
Yes, I can. Thank you very much for the introduction. Just going to enlarge this. So I hope you can see my screen now.
Perfect.
Perfect. Okay, so yeah, I'd just like to share some of the research that we did in the past 2 years on distributed L-band radiometers in low Earth orbit. Now, our objective with this investigation was to investigate the possibility of increasing the spatial resolution of L-band radiometers by creating large arrays from really dozens of free-flying satellites. And I was happy actually to see the ESMO's next concept in this afternoon, because I think the concept that I'm presenting is actually similar in many ways. So the first question is, why do we need better spatial resolution? This is a question that actually was answered very nicely, this afternoon. It basically, if we had better spatial resolution, we could improve a whole range of existing applications like sea ice localization up to better high resolution maps of soil moisture. Now, as we know, in L-band, it's not easy to really extend the spatial resolution because we need larger baselines, and that means that we also need a larger array. And existing satellites like SMOS are already pretty large, with a diameter in the order of 8 meters. So that just leaves us with either having large monolithic arrays or really going towards a distributed concept. And we've investigated the ladder here from an orbital mechanical perspective. So the basic idea is to extend the longest baselines by putting receivers on individual nanosatellites that fly in very close proximity to achieve satellites. Now, we're talking about distances that are below 200 meters. So dozens of satellites with very, very small distances. So the idea is not new, but we just found that it hadn't been explored from a system feasibility aspect. So the concept, it involves just a chief satellite that carries a Y correlator, just like a small version of SMOS. And it also carries a dispenser unit that would then dispense a larger quantity of deputies. That's what we call the small nanosatellites. That would be, as we envision them, 20 centimeter cubes or 8 U CubeSats that all carry an individual patch antenna. And we would place that the system would operate under the same orbit, basically, than SMOS does. So the main challenge really with designing such a system is defining actually the relative orbital elements of these small deputy satellites. Because you have to take into account two different aspects of the system. On one hand, you have the system feasibility aspect. You want a long lifetime, which means low fuel consumption, but also low probability risk. And on the other hand, the positions of your satellites also determine your area in the end. So I've just put this animation here to give you an idea of the design space that a designer of these orbits is working with. So the main challenge is choosing the relative orbits which give you the best of both worlds. And a solution that we've been investigating for this problem is to place the deputies on general circular orbits, or GCOs. This is a type of relative orbit that's defined by a circular motion of the deputy satellites within one common relative orbital plane. You can see here an example with only 3 deputies. The real system would have more. This is just to show the type of the orbit. GCOs, the general circular orbits, have 2 properties that make them very interesting for this type of application. First advantage is that the relative orbital trajectories are circular regarding the observation direction, so regarding boresight. That means that the baseline lengths between the deputies remain constant. In this example, you would just have a triangle that kind of rotates around boresight. And that gives you the advantage that you have a similar area around over latitudes if you can find a receiver configuration that actually delivers a circular symmetric array with lots of deputies at any time. The response then would not change because it would again it would only rotate around boresight. The other real advantage of using these GCOs with defining like this type of swarm-based radiometer is that it reduces the dimensionality of the problem. So instead of having to use 4 coordinates to define the relative orbits, you actually only have 2 because you can define positions within this wide 2D. Yes.
Sorry, I think your screen has frozen for the last. At least I only see chart number 2.
Yes, looks like it. Oops. We lost him.
Yeah.
Please, the organizer, can you help?
Yes, but it seems he disappeared from the list now.
It seems to be disconnected.
Disconnected, yes. Yeah. We can try to wait for him 1 minute. We have the backup presentation in case of screen sharing problems, but we cannot do anything if he disappears.
Of course. Joel Johnson, would you be ready? Oh, here is back now.
Here is Mark, yeah.
So I apologize. I might just stop my video to make it a bit more robust. Can you hear me?
Yes, we can hear you now.
Okay. So I apologize. I'm gonna
no problem.
Give you. Can you see my screen?
Yeah.
Yes, we can see it now.
Okay, so I'm not quite sure what you heard last.
We're hearing you, but we were not seeing the screen anymore.
Okay. So I was talking about the GCO orbits, where allowed the distribution of different deputies within one plane and the optimization of deputy positions within two coordinates. So the question then remains, how do you now optimize these positions within the plane? For this, we've actually used a numerical optimization method that we've borrowed from the design of astronomical telescopes. Now, the positions of the deputies are chosen in a way that actually optimizes the sampling of the spatial frequency coverage. The method works by minimizing an objective function according to an algorithm. And this objective function actually weights each spatial frequency sample by local density and by distance to the center. So what actually happens is this: the optimizer kind of spreads out the spatial frequency sample, and it selects the position of the satellites accordingly. So we've conducted simulations with this, with up to 96 satellites. And I just want to show you some results up to 32 satellites. And now you can see we're just looking onto this relative orbital plane. And you can see just how the deputies kind of cluster around the central Y satellite. It's quite interesting to acknowledge also that the optimizer doesn't choose a circle or a low triangle, but it actually puts them on one side. Now, this is because the optimizer actually is trying to get a lot of small baselines, because we've also introduced constraints, positioning constraints of the satellite, like a minimum inter-deputy distance and a minimum distance between the chief and the deputy. Actually, in this case, we say 10 meters as a minimum chief to deputy distance and 3.5 meters as inter-deputy distance. So now we can look at the spatial frequency coverage, which is a good indicator of area coverage. Now, again, since we're observing the target area over the entire overflight, we get lines aligned for each single baseline. And two takeaways here: you see obviously a denser coverage of the spatial frequency domain, and you see it also getting larger, so the diameter is larger. Now we can use a non-uniform Fourier transform to get the point spread function to actually show how our array response would look like. And there are also two takeaways. You get a better spatial resolution, smaller main beam, but you also get decreased side lobes. And because we have a very irregular sampling of the spatial frequency coverage, you actually don't have a larger side lobe. You have just a carpet, a constant carpet of remaining side lobe residuals, you could call it. So finally, I'd just like to look at how the key array metrics evolve with increasing number of satellites. So with configurations with more satellites, you can see that the more satellites you add here on the left side, you actually decrease the side lobe level. You also decrease the main beam efficiency, which is around 70%, still below monolithic areas, which are, let's say, 80% and above. And actually, this decrease in main beam efficiency comes because the ground resolution decreases as well. Now we would receive a ground resolution of around 7 kilometers for, to be honest, a quite big swarm of 96 deputies. Last thing I wanted to point out is the radiometric sensitivity, which is a bit of the caveat of the system, because we've used a uniform weighting technique to actually achieve a very nice beam despite the irregular sampling. But this also degrades the radiometric sensitivity. So you can also see that even with 56, 64 deputies, the sensitivity is quite low. But we're quite optimistic that we can, I'd say, improve that a bit through just an optimized weighting and maybe the tweaking of some other parameters. Right, so just to summarize, what we've done here is we've looked at the system feasibility and the imaging performance of a satellite swarm-based aperture synthesis radiometer in low Earth orbit. We've designed a methodology that was that they can kind of be used to define the orbit design of these small deputies. Conclusions are that it's generally reasonable that such a distributed L-band radiometer can be built. We need to improve the beam efficiency a bit. We definitely need to improve the radiometric resolution, which is definitely a problem with this system. Just the radiometric sensitivity will always be definitely lower than with monolithic systems. And of course, a lot more research has to be done on a lot of other aspects because we've only looked at the orbital mechanics aspect. So that's it from my side. I hope you still hear me. Thank you very much for your attention.
Thank you very much for this very attractive instrument to overcome the spatial resolution problem at 1.4 gigahertz. Any question from the audience?
May I ask a question?
Sure.
This is Nazareno speaking. Probably I have missed this information, but just to recall, which is the distance among different deputies, the average?
Yeah, we've used 3.5 meters as the inter-satellite distance. Now, I know that this sounds very, very small, and actually we've done also simulations with larger distances. But considering, let's say, where the nano-satellite technology is evolving, it's actually like very highly accuracy formation flight, let's say within 1 meter, has actually been demonstrated already. Of course, it's something totally different to control a swarm, but it's to us it's not so unrealistic.
Okay, thank you.
But we might need to increase the distance if the collision probability is too high.
Any other question? Oh.
We have a question on the chat.
Yeah. So to what extent do you think such large constellations are feasible given the constraints on station keeping and the risk of a non-cooperative deputy causing issues in the constellation?
Yeah, this is actually a very good question. And the risk is, of course, very there that sometime amongst the lifetime, one of these large amounts of deputies just gets defunct. And the solution to that is something that we're also looking at. Probably you will need to slightly tilt the GCO in the orbit around the radial direction, so the aerodynamic pressure will just push it out of the configuration. It will change the area performance slightly, but not significantly. This is a good question. Yes.
From Roland Albers, if I mispronounce the name, sorry. Any other questions? Okay, thank you very much. So let's move to the next talk, which is about very low microwave frequencies now, by Joel Johnson.
Yes, thank you.
Can you share your screen, please?
Yes.
Perfect. Oh, great.
Okay, how does that look?
Perfect.
All right, thank you. So yes, this is a talk about microwave radiometry from 500 to 1400 megahertz, which we think is an emerging technology for Earth remote sensing. This is joint work with a large number of collaborators, as you can see on the list of authors here, reflecting the growing international community that's exploring these ideas. So, and over the past decade or so, we've seen multiple publications and experiments reported that have demonstrated performing Earth remote sensing using frequencies in this range, as well as some older work as well that's explored some Earth remote sensing using frequencies lower than a gigahertz. At such low frequencies, we have advantages over higher frequencies in terms of penetrating more into geophysical media, in terms of the sensitivity to some particular products, as I'll talk about in a minute here. But of course, there's no protected spectrum in this range, so definitely RFI is a huge challenge. These are heavily used bands, So any instrument has to be designed to deal with that situation and try to perform thermal noise measurements in the presence of interference, which means that we have to shift our perspective here that these are more opportunistic type measurements. If we have a mission, we may not be able to measure 100% of the time, but we can measure some fraction of the time, and the value of the measurements that we get in those situations still motivates doing these kind of measurements. And as you might imagine, success might be more likely in less populated regions, for example, over the global oceans or at high latitudes. Additional idea of working in this frequency range, including extending up to 2 gigahertz, is that if we measure not only the emissivity or the brightness temperature at one frequency channel, but over a range of channels, we can do a sort of hyperspectral sensing by looking at the spectrum of the brightness temperature to try and get additional information on the geophysical parameters we're interested in. So the goal of this talk is just to kind of review what's been going on in this area, talk about why we might want to do this, and talk about the challenges, the opportunities, and recommendations for future work to keep this area progressing. So first, I want to just review a few of the potential geophysical products we might be interested in using these low frequencies. Land products, there's of course soil moisture is one of our land products we're interested in. As we go to lower frequencies, the penetration depth will be greater. This is a plot showing the change in penetration depth from a simple dielectric constant model at nadir as a function of frequency. And as you can see, we have curves that increase here. The rate of increase depends on the particular soil moisture content and soil conditions. But we should expect that we should penetrate at least somewhat deeper into soil at lower frequencies. And Jeff Walker's group in Australia has been experimenting with this. On the right-hand side of the chart, we can see some airborne measurements that were conducted, including both L-band, a 14, standard L-band radiometer, as well as one operating at 750 megahertz. And the first results of this are first that you can measure the thermal emission at 750 megahertz. It's not totally washed out due to RFI. And you do see different geophysical signatures in the two bands that his group is exploring and trying to interpret in terms of different sensing depths and different penetration through vegetation. In addition, you could also potentially sense different properties of permafrost or freeze-thaw properties, including the thickness to which the freezing occurs in the soil. So the land products are of interest. Another potential product, as we've been hearing about, sea ice thickness is a product that's of interest for microwave radiometry and has been demonstrated using SMOS and SMAP measurements at 1.4 gigahertz for relatively thin sea ice. Here we have a plot here showing how the brightness temperature might vary with sea ice thickness at different frequencies, from 500 megahertz to 2 gigahertz. And as you might expect, the lower frequencies show a more gradual increase in brightness temperature with ice thickness, so that there's the potential to extend the thickness range over which you could sense thickness information. So that's the idea here. We'd like to be able to sense sea ice thickness over a wider range of thicknesses than we can using just 1.4 gigahertz alone. We've done some demonstrations of this with an Ohio State system called MicroRad that measures between 500 and 2,000 megahertz over sea ice north of Greenland, where we did retrievals of thickness that we think demonstrate this idea, as well as trying to simultaneously retrieve both thickness and ice salinity, again, from the spectrum of measurements that are obtained. Another potential geophysical product are the temperatures inside of ice sheets. Giovanni Massoloni and the group at CNR have done some demonstrations of trying to retrieve temperatures inside of ice sheets using just small measurements alone. And they've shown what can and can't be done there. You definitely can make some progress there. But by extending, again, over a wider range of frequencies, and measuring as a function of frequency, you can kind of take the idea of temperature profiling in the atmosphere by measuring brightness temperature as a function of frequency, and extend that into temperature profiling within an ice sheet by measuring brightness temperature as a function of frequency. And here we have plotted, if you generalize that concept into a weighting function, you can think about, the brightness temperature you observe as an integration of the physical temperature of the ice sheet over a weighting function. These are the weighting functions that can occur in some situations. Here's an example for the Dome C type temperature profile, showing that indeed different temperatures give you different sensitivities to temperatures within the ice sheet as a function of depth, so that by making multi-frequency measurements, you can try to infer the temperature profile. We've also have some measurements from the UWB-RAD system in Greenland that acquired multi-frequency measurements along this flight path between borehole sites in Greenland, along which we attempted to retrieve the temperature profile inside the ice sheet shown here. And we've got an accepted paper in TGARS that'll be out soon to provide more information on those results. Yet another potential product of interest is the salinity of the ocean, the sea surface salinity. As we know, that's done very well at 1.4 gigahertz, been demonstrated by SMOS, MAP, Aquarius missions. But those missions have reported that in cold waters, at high latitude waters, for example, where the temperature is near 273 Kelvin, you get a degraded salinity retrieval performance that results because of the reduced sensitivity to salinity in brightness temperature that occurs at different frequencies. So 1.4 gigahertz in cold waters, we have a reduced sensitivity to salinity, as you can see here. If you were to vary the frequencies to lower frequencies, you can restore some of that lost sensitivity and thereby hope to improve your sensing performance for retrieving sea surface salinity. What's shown on this plot are some results presented at the last MicroRad from simulations performed by David Levine and Emmanuel Dinat at the Goddard Space Flight Center, showing how these high salinity retrieval errors, these are plots of simulated salinity retrieval errors, how the increases at high latitudes might be reduced by adding additional frequencies, for example, a channel at 800 megahertz. Again, because of the improved sensitivity to salinity that occurs at these lower frequencies in cold waters. So those are some of the motivations for trying to pursue measuring at these frequencies. So there's definitely some good motivations here, but there's also a lot of challenges, as you might expect. One of those is the antenna size. When we go to lower frequency, we need a larger proportionate aperture to maintain the same spatial resolution. So that's certainly a challenge. But the technology of large deployable reflector antennas has many applications outside of remote sensing, and it's continuing to advance. And so that reflectors are being deployed in space these days that are much larger than those that have been deployed in the past to the scale of 10 and even 20 meters. So that this is a technological challenge that seems addressable given that development. And those technologies are producing manageable costs, stowed volume, and mass for deployment from reasonable sized satellites. For example, the MicroRad Earth Explorer 10 proposal led by IFAC proposed a 10-meter class large deployable reflector. And so these are feasible. RFI is certainly another challenge, as we shouldn't be surprised about that. This part of the spectrum is heavily used for many applications. But as we've heard in this conference, systems for RFI detection and filtering are improving, including those that can attempt to do this in real time. When we think about this part of the spectrum, definitely it's heavily used, but some portions of the spectrum are allocated for things like broadcast applications, which already have to share the spectrum. They have a certain TV channel is licensed to operate in one place, and then for a certain region around that, there's no other licensee. So there's sort of this spectrum sharing that already exists for some of these applications, also navigation or radar navigation type applications. So some of those applications, opportunistic radiometry has a better chance of coexisting with. And we don't have to necessarily measure over the entire spectrum, as long as we can get some portion of the spectrum. And if we can use, for some instruments, it's feasible to have a wide bandwidth and a long integration time, so that even if you lose a significant portion of the spectrum to RFI, you can still perform opportunistic thermal noise sensing in the part that's left, and thereby retain the ability to make some science type measurements in these bands. There's a couple of talks I wanted to reference coming Wednesday and Friday that talk a little bit more about this in this conference. If we're going to also measure over a wide band, we don't necessarily have to measure over a wide band, but if we wanted to do that, to do this spectrum type sensing, then we need to worry about how do we make such a wide band receiver. As we know, radiometers like high performance receivers with minimal reflections inside to be able to calibrate and produce a stable receiver. So that's a challenge, but there are multiple receiver architectures that are under development or being explored across different groups that address this, and components continue to improve as well. Here's an example from UWB-RAD showing the pseudo correlation type architecture that has shown some potential for this type application. There's a talk on that on Friday. Definitely calibration is still an important consideration for these wideband receiver types. And also, at these bands, the ionosphere and the celestial sources make important contributions. The impact of the ionosphere grows as 1 over frequency squared for some of its effects. So as we go to lower frequencies, those are going to increase. We need to be more precise about compensating the ionosphere and so on. Also, celestial sources, we need to worry about how do their emissions vary with frequency. And for some of those, the spectral coefficient is such that they have larger effects at lower frequencies. So we need to keep that in mind. One way to try and address that, for example, is if you could afford to observe at nadir in circular polarization, that's going to reduce some of the impact of the ionosphere, making its correction more feasible. And the information about celestial sources continues to improve over time. Here's an example paper about showing the frequency dependence of various celestial sources. So it seems that the progress that's been demonstrated for SMAP and SMOS in correcting these kind of effects can be extended into these lower frequency bands. So to keep this area progressing, we need to continue our research, learning more about spectrum occupancy and availability using license surveys and airborne ground-based spectral surveys and so on are important. Continuing to develop the required component technologies, receivers and antennas, and the architectures of the receivers, continuing to advance RFI detection and filtering methods. Continuing on the science side to advance our knowledge of the permittivity of geophysical materials in this frequency range. There's a lot of data out there, but any additional information we can get always helps. Trying to predict the emission spectra we should expect in these ranges for different geophysical media. There's a lot of modeling work that's going on, but additional developments are, of course, important. And continuing to perform ground-based and airborne demonstrations over a wider range of scene types and conditions. And also, continuing the science story of how these new products we could potentially produce might impact science results across various disciplines. So in conclusion, we think that this area has been advancing over the last several years. We think it shows the promise of this idea and the potential that could make. Definitely there are the challenges we've talked about, so continue to work to address those as recommended with the goal of having a system like this operating in space sometime in the near future. Thank you.
Thank you very much for this very inspiring demonstration of the interest of these low frequencies. And actually, I have a comment for you because we are deeply involved in the SIMR Copernicus mission. And I wish we could have this type of receivers on board. And not only it helps for all the products you mentioned, but it could also help for sea surface temperature retrieval, because especially over low surface temperatures, we have trouble around 6 gigahertz, and we would like to have lower frequencies for this. So congratulations for this work. So any other questions and comments? I don't see any on the chat. Any on YouTube?
Joel, can I ask one thing?
Yes.
So do you have any idea to propose these kind of things to the NASA next mission or anything?
Yes, there are currently various mission proposal ideas in process. So, and it depends on the time scale, the opportunities that exist, but certainly there's a lot of interest in that, and we're looking at mission proposal opportunities, yes.
Great.
Okay, thanks.
Joel, one question.
Yes, please.
Steen Saustrup. Just wondering, I mean, when you go to that broad frequency and you go into the satellite, like SMOS, when SMOS was launched, it saw a huge, almost anywhere within the horizon, RFI sources. Isn't you simply going to get saturated with such a wide receiver, or how are you intend to deal with that?
Certainly, the potential for saturation is an important aspect of the receiver design. And, various ways, certainly you need to have some receiver protection early in the receiver. And then generally you'd want to sub-channel things as early as possible so that if one channel were to saturate, it wouldn't impact the other parts of the frequency range. So those are some of the trade-offs of the different receiver architectures.
Thank you.
Thank you very much. Okay, Frank, do you want to take over?
Yeah.
Great.
Yeah. Thanks, Catherine. And so we are ready to go on and quite in a good time. So we can proceed with the next presentation. The next presentation is about validation of geolocation accuracy for millimeter and sub-millimeter wave radiometers. And the presenter will be Dr. Mario Papa. So please, Mario, the floor is yours.
Hello, do you hear me? You see my screen?
We hear you and we see your screen. Thanks.
So I'm Mario Papa from the University of La Sapienza, and this work aims to propose a methodology to validate the for the frequency 100. This presentation. First of all, the location for the future ICI of the government that they will be on board. Yesterday, in the presentation by Vino Mattioli, this radiometer has 11 channels with frequency at 183. The usual approach to validate the geolocation consists in the comparison between the high brightness temperature contrast along coastline. For example, in the top you can observe this for a low frequency at 19 GHz. But for 183, this contrast disappears because the water emissivity increases and the atmosphere is less transparent. So the surface find other landmark target or reference. So the methodology that we propose is similar, but we introduce two other kind of reference, not only the Chevelang database, but the SAR image, the synthetic weather images, and the digital elevation model, in order to exploit this frequency factory. This is the scheme that shows the simplified step of the methodology. In particular, the right branch describes the reference tools, and the left branch describes the satellite images. In particular, the first question is to understand if the target is on surface level or not, because in case present of oil or other mountain, the line of sight intersects the orography in a different point because the satellite coordinates are projected on the ellipsoid. So we have an incorrect location, and this can introduce some error in the geolocation of the pixel. These slides better describe this correction. In particular, the blue marker represents the line of sight of the satellites, and the cyan marker represents the latitude and longitude on the ellipsoid. But this line of sight intersects the orography highlighted by the 4 pixels provided by the digital elevation model, and the intersection is highlighted by the green pixel. So the correct position on the ellipsoid is the magenta marker. In the right figure, it is possible to observe the satellite track with the red markers, and in magenta all pixels that we correct in this way. To landmark target, because as I told before, for example, the Libya coastline disappear at 180 GHz. So we must understand which are the main parameters that influence the brightness temperature contrast. So considering 2 adjacent pixels with homogeneous isothermal thickness of atmosphere, is it possible to observe that the transmittance, the surface emissivity, and the surface temperature can be the most important parameter for this contrast. We focus in high altitude lakes, for example, the Qinghai Lake in Asia, the Titicaca Lake in the Southern America, and to exploit the dependence in the brightness temperatures by the surface temperature, we focused also in the mountain chain with great slope. For example, the Karakau mountain and the Andean chain. In addition to exploit the area with lower integrated water vapor, we focused on polar region. In particular, in the Arctic polar region, we find the Nares Strait in the northwest part of the Greenland and the Anson Bay in the northeast part of the Canada. And in the Antarctic region, we focus on the Antarctic ice shelf, in particular the biggest three ice shelves, the Ross, the Falkland One, and Amery ice shelf. This figure shows these three ice shelves, and particularly in the Antarctic region, the ice is attached to the ground and descends into the ocean, creating this big platform of ice. And at 180 gigahertz, this shelf appears colder with respect to the adjacent sea. But we have a problem because this ice coastline can change along the year due to the variation of the season, or for example, it can collapse, creating some icebergs. So it is important to monitor this ice coastline, and we propose to use the SAR image because it provides this coastline with very fine spatial resolution. For example, in this area, we use the SAR image in extra wide mode with a resolution of about 40 meters. This is an example in the comparison. In the top, you can find the SAR image in the Rosa shelf, and the red line is the contour extracted from this image through K-edge detection algorithm. In the bottom, you can observe the radiometric image provided by SSMIS at 183 GHz in horizontal polarization, because this is a satellite with a frequency similar to the future ACI. And cross-correlating the extracted contour from SAR and the black marker that represent the extracted contour for the radiometric image is possible to reconstruct the shift of the image and validate the geolocation of the, in this case, of SSMIS F17. This is an example of a Kingai Lake in which we cross-correlate the contour extracted for the radiometric image at the shoreline database. Here is the comparison between the brightness temperature in the top and the digital elevation model in the bottom, because in this case the Mount Change has a very gradual slope and the surface temperature decreases very fast with the altitude. So these decreases appears also in brightness temperature. So cross-correlating the gradient between the gradient of two images is possible to reconstruct the shift and validate the geolocation using digital elevation model as a reference. So final number of our tests. To test all targets, we use SSMIS F17 for all 2016. It is very important to have target both in North Hemisphere because we see the surface this frequency, especially during winter season, because we have a lower value of integrated water vapor. So it is necessary to have some target in the north and some target in the south hemisphere. But it is possible to observe that the number are almost stable, around 4-5 kilometers, depending essentially in the shape of the target, because, for example, a closer curve can represent very well the shift along both directions, along coast and along track direction. Instead, some other target, for example, there was and we saw before as an horizontal line, so it can reconstruct very well only one direction. So, putting together all these numbers, error in the geolocation from this instrument is 4.8 kilometers with a standard deviation of 2.1 kilometers, and this is very similar to in other work, in particular that use lower frequency. For example, in some other work, use 19 and 18 gigahertz to validate this instrument. It's very important to know that the future ICI has on board also the ICI4, such as 243 GHz, and this is a Windows channel, so it is very important to further investigate this frequency because we could see better the surface, increasing the number of target and maybe increasing the number of sample for the validated the geolocation on all years. Also that in the polar region, because SMIS has a polar orbit, the number of available samples are very high with respect, for example, to Titicaca Lake, that this is a target near the equator. So that's all. Very much for your attention.
Thank you, Mario, and, for this nice presentation. Are there questions from the audience, both in the chat or on YouTube?
Frank, we don't have a question from YouTube at the moment.
Okay. Thanks, Emanuele.
Hello, this is Nico Cimini. Maybe I have a question.
Please.
Looking at the slides you showed about the Titicaca Lake, there seemed to be a kind of a orthogonal coastline between the SAR image and the radiometer. So, can you comment on that? Why?
Whoa. What slide did you refer to?
There was one on the Titicaca Lake.
This is
no.
Titicaca
There was
Lake?
an image. There was an image. This one.
This is the Kingai
sorry.
Lake in Asia, not
So you see the one on the left.
Okay.
Okay, sorry. So the one on the left, you see the coastline. It seems like there is a kind of a orthogonal coastline with the radiometric contour with respect to the database. So maybe
yes. Maybe.
So yeah, can you comment on that? I mean, why we see that kind of canyon there?
Okay, note that this radiometric grid is not the original, because to try to find a sub-pixel accuracy, we interpolate the original image in a grid of about 5 kilometers of spatial resolution. So if you can observe, the shift is almost 1 pixel, and with the final number of the errors of SMIS. And the direction of the shift is main in the along track direction for the Kingai Lake, because this lake and Titicaca Lake are near the equator, so the error is almost in the long track direction and not the cross track direction.
Okay, thanks.
Welcome.
Okay, thank you. And so we can move on to the next presentation. And the next presentation is about atmospheric boundary layer observations for atmospheric applications. And the presenter is Marian Klein. So please, Marian.
Okay. Presentation, I will put it to the first slide.
Yeah,
okay, am I allowed to start right now?
Yeah, we see the presentation going on.
Very
Thanks.
good. Very good. So I will be talking about atmospheric boundary layer observation for operational meteorology and climate. This is a issue which is becoming more and more important for the current meteorological observations. Yeah. Somebody smart. Okay, so how do I get to the next slide? I don't know.
I'm trying to.
Yeah, I have a problem of getting to the next slide for some reason, but
Okay.
yeah, let me try this. Yeah, okay, that works. Yeah, okay, very good. So planetary atmospheric boundary layer or planetary boundary layer are basically synonymal terms that are used for the description of the lowest level of the atmosphere, basically, that interacts with the surface. That layer of the atmosphere is showing here on the left side with the different structure as it changes between sunrise and sunrise, so 24 hours period. And on the right side, I have a picture of the view of the Salt Lake that shows that atmospheric boundary layer as it traps the atmospheric things below it, and then basically have a free atmosphere above that. And the height of this atmospheric boundary layer changes between a few tens of meters up to 4 kilometers or more. And the way how you determine it is there are several methods that are used in meteorology, and they are actually part of the, they are described, for example, in this paper, which is shown here. So who needs that measurements? So for example, NASA has PBL, Planetary Boundary Layer Incubation Program, which is the goal, and that was identified as a decadal survey that shows that this is one of the priority for the for the observations and for the future flight in the implementation. But they're also looking at observing system architecture that are utilizing airborne or ground-based observations and other things. What does it mean to measure atmospheric boundary layer? It means that you need to measure vertical profiles of water vapor within the planetary boundary layer in the cloudy conditions, or vertical profile of the temperature within the planetary boundary layer in the cloudy conditions. And then planetary boundary layer is derived from those measurements. Another synergistic measurements that NASA is looking for are highlighted here of what the radiometer can do, and those are cloud properties, liquid water path, precipitation type, and rate. And then other thing that they are looking for is the profile measurements of water vapor and temperature that extend above the planetary boundary layer. Another need is for the atmospheric boundary layer or planetary boundary layer measurements are from other renewable energy sources. For example, this is a paper that was published in the October in the Journal of Science, and it shows that one of the grand challenges of the wind energy is the understanding of atmospheric wind and power plant flow physics, which includes, and it is very important to measure, how stable is the atmosphere. And again, stability of the atmosphere is determined by the by the temperature and humidity profiles of it. And when I talked to one of the authors of the book of the paper, it shows that a few sparse observations. This is not what will make any difference. They have a desired vertical resolution about 20 meters and resolution in time about 10 to 30 minutes. Sorry. And 1 hour for forecasting energy production. And boundary layer profiles, what are of interest for them, is at least up to 300 meters. Sorry. You can do measurements also in the offshore wind farms, which again, the number one need for offshore wind farms for the future is more measurements from the temperature and humidity profiles. They need more observations, and you can do these measurements by doing, things like, for example, the meteorological mass. But they have their problems, as I am showing here on the right side. Who else needs the boundary layer measurements? Is operational meteorology, which could improve the observation of the severe weather events and also localize mesoscale weather forecast. And almost every area of economy benefits from improved weather forecast, and better measurements are happening by having more better observations. So again, what is if we return back to what needs to be measured is vertical profiles of water vapor and humidity, and water vapor in planetary boundary layer, and vertical profiles of temperature. So the microradiometer is an ideal tool for this because it measures that thing, temperature and humidity profile, cloud liquid water content, integrated water vapor path, precipitation type and rate can be also measured, and other things that are important for weather, like for example, supercooled liquid detection can be done by the microradiometer. And I'm from the perspective of user, surface-based sensors are closer to the atmospheric boundary layer, planetary boundary layer. So why put it on the satellite somewhere 300, 500, or 800 kilometers away and then do these measurements? And microradiometer also provide measurements in all weather conditions, ideally. So why passive microwave sensor? I have here images of the scattering and how it looks in optical spectrum. So if we look, for example, in Rayleigh scattering, that means that the wavelength of the observation is much larger than diameter. Then it is similar to the blue sky that you see on the in optical spectrum. If you look at the Mie scattering, where you look at the atmosphere, that's something like a fog. But in both cases, microradiometers can penetrate the atmosphere and can see through the clouds what is behind them and what is on the other side. Non-selective scattering is when the observational wavelength is much shorter than the diameter of the particles, and that happens in optical spectrum and far less in the microwave, again, depending on the wavelength. And microwave sensors that are currently on orbit are regularly evaluated as having the highest forecast sensitivity observation impact for weather prediction. This is the ECMWF plot between 2012 and 2019, as you can see. And it shows, two microwave contributions where the dark line is microwave sensors for wet situation, they call it, which is the water vapor and cloud and precipitation, which is this dark line here. And then for the temperature sounding, which is this red line on the top. But consistently you can see that microwaves contribute roughly about 40% to the forecast observational impact. So that means, the rest of the observational principles that are currently used are contributing the other 60% or less than 60%. That includes all ground observations, all aircraft observations, radio sounds, and everything other that contributes to the observational. And there has been history, that's why that black line is going up. But basically it means, like, for example, if you do all sky assimilation of the channels of the microradiometer, then the contribution jumps up. And there is a part which is incorrect results. Sorry, let me return one slide more. So this is the current weather observing network according to the World Meteorological Organization. And I had the quiz question. Sorry that we cannot really answer it, but please try to find a ground-based radiometer here. And of course you cannot, because nothing observational actually exists for the ground-based radiometry. And it is amazing to me that the meteorologists who love microradiometers observing from the space, and they are such valuable instruments to provide and improve meteorological observation from the space, are not pushing for anything on the ground. As you see, there are plenty other sensors that are being used. Why radiometers? Again, there is one more point that I want to make, and that is, that globally the cloud fraction derived by the MODIS cloud mask is doing 67% on average. So that means, that 67% of the planet is continuously covered with clouds. So if you use any other wavelength which is shorter than microwave, then you would build an instrument which is in the best case, going to operate at 33% of the time. So how could that thing operate, or how would that be working? So I have here a cross basically track scanning radiometer, like for example ATMS, and its width of the 2,600 kilometers. And if we assume that we will put a network of the ground-based sensors, which is 200 kilometers spaced apart, as it is shown here, then you see that each green dot represents the ground-based sensor. This is the swath of the ATMS, which takes about 0.8 seconds to execute. Here are different footprints for different channels of the ATMS. But basically, the whole image is about 10 minutes here, or 11 minutes approximately, and there are 336 interactions between the ground-based and spaceborne radiometers. So that means, that even the ground-based radiometer can be used to support space observations, because it can actually bound the retrievals a little better if it is done from both sides, from the ground and looking up, and from the space looking down. So it's gonna be expensive. And yes, people will point out that yes, something like that is gonna be expensive. So what I use here some preliminary, rough estimates. So let's say that the cost of the hardware for the ground-based will be approximately the same as for the new satellite mission, which is about $1 billion. Sensors would be spaced of 200 kilometer grid apart globally, including everything, oceans and polar regions. Then the total number of the sensors would be about 12,000, 13,000 approximately, which leaves the cost of the individual sensor to be about $55K and installation about $23,000. So the total cost per site would be $78,000. So yeah, it's expensive. But if we look back on the history of the satellite remote sensing, first satellites for the Earth observation are dating to 1970s. And a lot of development has happened since. There have been a lot of investments into that field. Even new field of the satellite meteorology now exists. And it wasn't inexpensive, and it wasn't easy, and it came with a lot of efforts too. But I believe that with same effort in engineering, algorithm, data, assimilation, and others, we can also achieve similar things. And again, comparison with Raman LiDAR, with infrared radiometers that are working only in partially under the clouds. Radiosones, which are favorite instruments of meteorologists, if you consider just the consumables per one launch, it's about $250, but annual site per consumables operation is $182,000, and that's only for 2 profiles a day. So there are challenges. There would be challenges to do something like that, because every sensor would have to be basically individually developed. That means sensor is the radiometer that operates, or the radiometer receiver that operates on certain frequency range. Sensors must be simple, built economically, small and integrated, must be able to operate over the long period of the time, for example, 3 to 10 years, similarly as satellites do. It has to work reliably over ambient temperature variations. It has other parts of the system will have to be developed, something like antennas, aperture protection, scanning, if scanning is involved in motion system, data acquisition system. We even don't know for the ground-based radiometry if the aperture size has better influence on the profile in the lowest level of the atmosphere than the range of the frequencies that are used on vertical calibration. And then other thing is that the calibration must be without human presence, because otherwise it's not gonna be practical to using calibrating 12,000 sensors. And testing this radiometer system will have to happen under different conditions. So my point is that we need to lobby meteorological community for development of such sensor. Meteorologists do not know what these sensors could provide them. And we know that there is no other better technology that can do this planetary boundary layer profiling under weather conditions. Global distribution of sensors is possible, but if you do that, then you can have a revisit time of 2 seconds, possibly. And again, this is just make a point, before I go to questions, that, this is, for example, comparing two meetings. So this is a ISAT-2 collaborators. You see that number of people there? This is the deployment of the ground-based radiometer in Alaska. I'm not saying that 2 people were responsible for that. There was about a group of 20, but this still doesn't compare even on scale between those 2 things. So that's the end of my presentation. Thank you very much for your attention.
Thank you, Marian. We are a little bit ahead of time. So there is a time for one quick question. Any question from the audience?
I have a question, if possible.
Yeah, please, Nico.
Hi, Marian. Of course, I fully copy your crave for more ground-based providers, and I hope that you will be able to see my presentation on Thursday, because you will be pleased to see the what we are doing in Europe. But the question is, so what will be your solution? So do you see instruments that are getting cheaper for mass production and mass distribution, and what would be your perspective in this direction?
Yeah, I think technology is available that can make this much less expensive, especially if you have advantage of scale. Because if you are building, let's say that you are operating 13,000 units worldwide, and you have then 3 years, let's say 5 years, you need to exchange each of them. So that means that you are changing thousands of instruments annually or maintaining them. So you can really develop infrastructure that will support something like that. And I think it will be much smaller infrastructure than it is today for the spaceborne sensors. So I think this will be perfectly doable from the economical standpoint of view and from the functionality standpoint of view. It's just that it will take some initial investments into the system, such that things like that could be evaluated and born. So if you have satellite mission that takes 10 years to develop, why cannot we have a ground-based mission that will also have a luxury of funding and development for an extended period of time, so we can actually see what could be done and how?
Thank you, Marian, and for sure a good topic for a roundtable about the future of radiometry, from space into the ground. So we can go on.
I have a question, Frank. Just a short question, a very practical one. How do you handle this type of instruments over the ocean?
A buoy. It would be sitting on the buoy. But again, there has to be some chance to determine, whether that buoy has to be 1 meter or 10 meter in size, or how would you do it. But I think that initially you can put them on every available island just to do, or close to the shore and close to the available islands. But I mean, the buoy is the solution.
Okay.
Thanks again, Marian. So we can move to the last presentation. We have a few minutes of being we're a little bit late, but still the last presentation, but not the least. And the topic is about MicroRad imager for METOP 2nd generation, development status and the instrument verification. And the presentation will be given by Tito Lupi. So please, Tito, the floor is yours.
Yes, thank you. So good evening and good morning still for some of you. So we come back now to a big satellite mission. So NWI, as you heard already yesterday, is one of the instruments of the METOP SG satellite mission.
Tito, we don't see your screen. I don't know if.
Sorry, I thought.
Yeah.
Just a second. I try again.
Yeah. Still, yeah, it's now coming up. Yeah.
Okay.
Thank you.
So, NWI is developed by a wide industrial consortium. The system team is shared between Italy and France. And okay, we have actually contributions from the industries all over Europe. I will give you a brief overview of the instrument design with some focus on some aspects. And then we will see where we are with the development and which are the results up to now, and then very quickly what are the next steps. So NWI, as you already know, is a conical scanning radiometer with 18 channels from 18 gigahertz to 183. And okay, actually 26 if we count for the double polarization of channels from 18 to 89 gigahertz. Okay, just I try to anticipate some questions. For the 22 gigahertz channel, we had a slight modification last year, if I'm not wrong, trying to avoid the RFI from G5 communications. So the frequency was moved from 52.6 to 52.7, and the bandwidth have been reduced from 400 to 180 megahertz. Obviously, this has some impact on the sensitivity, but this is the price. Okay, the main part of the instrument is the so-called MicroRad, which you see here, and in exploded view on the right. Plus, okay, we have other two electronic units in the satellite body, which are the control unit and the scan mechanism control unit. Okay. So the receivers have different architecture depending on the technology possibility, especially in terms of channel filtering and bandwidth, and on specific requirements. So in particular, the 18 gigahertz channel is an heterodyne receiver due to the fact that we need an intermediate frequency for the RFI processor that we have on this channel to mitigate RFIs. Most of the, or not most, some other channels have a direct detection receivers, so with filtering and detection directly at the microwave frequency, and for other channels we have heterodyne receivers divided in two units, so a front end with the down converter and a back end unit. The technology of the receivers is okay. Just okay. One word. All the receivers have an radio frequency LNA directly at the input to cope with the sensitivity and with the low noise requirement. And so this technology has been mostly developed in Europe and in very extensive effort has been dedicated to the qualification and to the assessment of the reliability of the receiver's elements due to the fact that the hardware for all the instruments, so we have 3 flight instruments that will be launched at 7 years or 7.5 years intervals, and they are all being manufactured in this period now, and they will fly up to close to 2050. So it's a very long lifetime. Also, a big effort has been done to characterize the reflectors, so the main reflector and the calibration reflector for NWI, to have a very good knowledge of the reflectivity and then of the antenna losses. And the same has been done for the design and characterization of the feed horns. On the lowest frequency channel, we have a radio frequency mitigation processor. So the algorithm have been developed by the Technical University in Denmark, and it is implemented on an Spartan 6 FPGA. The algorithm, the way of eliminate the RFIs is to divide, to sample the intermediate frequency signal at 500 mega sample per second, and then dividing with a filter bank the signal in 16 frequency bands and 8 time slots. And on each of these subpixel, we apply an equalization of the 16 bands to compensate for the unevenness of the receiver spectral response. And then we calculate the kurtosis of the samples. And this is compared with the threshold. Then we have, anomalous amplitude detection and cross-frequency comparison. And depending on the algorithm, we can have different performances. So red dots are detected and blue are undetected interference. And for different kind of interference and with the combination of different algorithms, we can have better performances. We had to face several challenges in the design. On the right, for example, you see the feed cluster and the front-end sub-assemblies. So most of the front-end receivers are integrated here, which is a subsystem of roughly 40 centimeter wide. And okay, then we had other challenges in terms of power consumption, mass, and so on, as usual for satellite-borne instruments. We developed also, let's say, supporting performance model, which models all the disturbances and the errors in the system, and it is used to predict the performances of the instrument and to allocate, at the beginning of the project, to allocate the requirements to the different part of the instrument. We have also a ground processor prototype and a performance assessment tool, which are combined also with an instrument data simulator to assess the performances and to support the verification of the instrument on ground and then on orbit. This is a sample of the output of the ground processor with let's see, actually of the end-to-end simulation with on the left simulated data and on the right the data reconstructed by the instrument and the GPP with some statistics of the result of the resulting difference. And previous one was for the 18 gigahertz, and this is for the 183 gigahertz channel. Coming to the development status of the instrument, so we had.
Vito, there are 2 minutes left.
Yes,
Thanks.
I will speed up. Thanks. So we had a structural and thermal model that was used to qualify the structure and the thermal design of the model, and it is used also for the first antenna measurement campaign that we will see later. We are now in the middle of the integration of the engineering model, and you see some pictures here, and this model will be used for the functional and performance verification, including the software and including test in thermal vacuum conditions. With a partially refurbished STM with flight feed horns, we performed the first antenna test campaign. We measured both the main antenna beam and the calibration antenna pattern in different scan positions, and we had good results. The main purpose of this campaign was to check the correlation of the measurements with the simulation of the antenna patterns, and the result is quite good. So we have very close results from the simulations, and this will help us for the next models. We have done a preliminary performance measurement, especially of radiometric sensitivity, gain, and spectral response of the receivers with this test setup of using, let's say, the deck of the instrument fully integrated with receivers and feed horns and with some cold and hot target in front of the feeds. And we have very good correspondence of the NEDT with the prediction, in some cases even better. And also the spectral response is satisfactory as anticipated. And okay, with just some small deviation, for example, here. Next step are the balancing of the rotating part of
Are
the.
you concluding, Tito? Just
Yes. Just
okay. Sorry, but we are a little bit late.
Yes, just the last slide.
Thank you.
And so then we will complete the integration, and then we will go to the functional and performance verification. This is the test setup for the performance verification in ambient with a cold target here, and in thermal vacuum with Earth target with variable temperature and a fixed cold target simulating the cold sky. Very quick overview of the schedule. So the EQM will be finished autumn next year. In parallel, we are already starting the integration of the proto-flight model, so the first flight model that will be finished mid of 2022, and the following two flight models 2023 and 2024. I finished. Thank you for the attention.
Thank you, Tito, for your presentation. One quick question from the audience and
yes,
the participants.
Steen Saustrup here. Hi, Tito. Thank you for presenting my material on the RFI process. What is the status of verifying that part? Because that's a new part for space in this context.
So the RFI module has been verified at module level using a white noise generator and a signal generator to simulate RFIs. And okay, the verification of the accuracy was quite difficult because you need a very stable generator. But okay, it was done at the end. And let's say the rejection and the capability of detection of RFI from the test is quite replicating what was simulated.
Okay, thanks a lot.
Thank you.
There are other questions. Indeed, there is another question from Pratik Kumar Dongre. How are you achieving a good radiometric accuracy and stability? I mean, this is probably too general to be discussed at this time. We have 12 minutes late, so I would actually suggest Pratik and Tito to keep in touch, so that if you don't mind, it's okay. Tito, you can see the question on the chat if you want to answer privately to our colleagues Pratik Kumar.
Okay.
So sorry for hurrying up.
No, it's okay.
So thanks a lot, and we are ready to close. So sorry for the delay, and thanks to all the presenters, and thanks to my co-chair Catherine Prigent, and to the organizers. And I believe that we have done for today, and so see you tomorrow at 2 p.m. Local time, Central Europe time, with the next for the first keynote session of this MicroRad 2020. Thanks a lot to everybody.
Thank you, Frank. Just a very quick reminder for tomorrow, but I am not able to share. So now possibly? Oh, yes.
Okay, now you're on. Yeah.
Okay.
Emanuele, yeah.
Just to remember, as Frank already said, we have the first keynote of this MicroRad 2020 at 2:00 p.m. Central Europe time. And tomorrow we will start with the two parallel sessions, the first on advanced techniques and the other on cryosphere. And at 6:30 p.m. we will have the radio frequency interference discussion. This is a side event that is open to all the interested participants. Okay, that's all.
The keynote will be in room 1.
As all the events, it will be in room 1, exactly. And for the presenting authors of tomorrow, do not forget to join the pre-sessions at 1:30 p.m. and during the break. Thank you again to the chairman, to all the presenters and all the attendees for this second day of MicroRad 2020. See you tomorrow. Bye.
Thank you very much.
Goodbye.
Thank you very much. Bye-bye.
Bye-bye to all.
Thank you
Bye
to
bye.
you. Bye-bye.
Good evening.
Bye-bye to all.
Bye-bye.
Thanks, bye.